A single point of light hides a dozen dancing suns. This is a duodecuple star system, a cosmic architecture where 12 stars are bound by gravity in one of the universe's most extreme and mysterious arrangements. By the end of this journey, you will uncover 50 strange discoveries that completely reshape what we know about stars, planets, and stability in space. We will see how a sky with 12 suns could exist, and why such a crowded system does not simply tear itself apart. What does such impossible complexity reveal about the nature of the cosmos itself? For decades, astronomers believed the sky was mostly filled with single stars like our own sun. The discovery of the first binary system, two stars locked in a mutual dance, was a revelation that changed our textbooks, but the universe had an even bigger surprise in store. As telescopes grew more powerful, we began to find triple stars, then quadruple systems, each one a more intricate clockwork of gravity. This progression led us to a strange and dusty place known as HD 98800. Often mentioned in the search for the most complex star families, this system is a crucial puzzle piece. It is not a duodecuple system, but a quadruple one. Yet it perfectly demonstrates the principle that makes even 12 star systems possible, the concept of hierarchy. In HD 98800, you do not find 4 stars orbiting a common center. Instead, you find 2 tight pairs of stars. Each binary system whirls around its own private center of gravity, and then those 2 centers, those 2 dancing points, slowly orbit each other across a much greater distance. It is a pair of pairs. This is the secret architecture of cosmic complexity. To build a system of 12 stars, gravity uses this same stacking method, creating pairs that orbit other pairs in a fragile celestial pyramid. Confirming such a structure is one of astronomy's greatest challenges. How do you untangle the light of 12 individual stars when they are thousands of light years away? Their orbits can span centuries, meaning we have only observed a tiny fraction of their full dance. One star might eclipse another, causing a dip in brightness, while a third star's gravity tugs the whole group in a subtle, predictable wobble. Astronomers must become detectives, piecing together clues from light curves and spectral shifts over generations. HD 98800 was our first real look into this layered reality, proving that stars do not just come in ones and twos, but in families built like nested Russian dolls. It set the stage, asking the monumental question: if 4 stars can arrange themselves this way, what is the absolute limit? How many dancing bodies can one gravitational melody hold together before the cosmic music falls into chaos? The theoretical limit of stability is a question that has haunted astronomers for centuries. With 12 massive stars all pulling on each other, the mathematics predict pure chaos. This is the infamous n-body problem, where calculating the motions of 3 or more interacting bodies becomes impossibly complex, a tangle of gravitational influences that should, by all rights, lead to catastrophic collisions or stars being flung into the void. Yet we see these systems persist. The solution lies not in defying physics, but in a specific kind of cosmic architecture. A stable duodecuple system does not place 12 stars in one grand swirling disk. That would be a recipe for instant gravitational anarchy. Instead, stability emerges from a strict hierarchy. Picture it as a meticulously choreographed ballet performed across vast distances. At the smallest scale, you have intimate pairs, binary stars so close they orbit each other in days. 2 of these tight binaries might then form a stable quartet orbiting a shared point. This quartet could become one component of an even wider system, linking with another similar group. The result is a nested series of orbits, a celestial matryoshka doll where each layer moves slowly and predictably around the next. The gravitational fury is contained locally within each tight pair or trio, while the larger system enjoys a relative calm. It is this separation of scales that creates pockets of profound stability within the apparent madness. The most likely configuration for a true duodecuple system would be something like 6 binary pairs arranged into 3 quadruple systems, which then all slowly orbit a common center of mass. In this delicate arrangement, the stars you share your tightest orbit with are your primary partners, their pull dominating your immediate environment. The influence of the other, more distant stars is felt as a gentle, steady tug, a background hum that guides your wider path but does not rip you from your partner's grasp. This hierarchical order is the universe's ingenious answer to the n-body problem, a way to build breathtaking complexity from simple, stable rules. It begs a fascinating question, however. If the stars themselves can find this delicate balance, what happens to everything else in that system? What becomes of dust, gas, and the very seeds of planets in a sky dominated by 12 different suns? This leads us to a third strange discovery, one that challenges our very image of these celestial families. When we speak of a duodecuple star system, the mind conjures a spectacle of 12 brilliant suns blazing in a shared sky. The reality, as astronomers are finding, is far more subtle and in many ways stranger. The confirmed candidates for these ultra-complex systems are rarely dominated by a dozen stars like our own. Instead, they are often a mixed bag, a cosmic menagerie where the faint and the failed outnumber the bright. A typical configuration might include just 1 or 2 main sequence stars, the familiar hydrogen-burning suns. Orbiting with them could be several red dwarfs, which are smaller, cooler, and far dimmer. The count might then be filled out by brown dwarfs, those mysterious objects often called failed stars because they never gathered enough mass to ignite sustained fusion. And in older systems, you might even find the ghostly remnants of dead stars like white dwarfs or neutron stars, silently adding to the gravitational tally. This means the duodecuple label often refers to the total count of significant gravitational bodies, not to 12 glaring beacons. It is a system defined by its total mass and complexity, not its visual splendor. So, the sky in such a place would not be a uniform, blinding brightness. It would be a hierarchy of light dominated by 1 or 2 primary suns, accompanied by a few dim, reddish companions, and completed by dark, nearly invisible giants whose presence is felt only through their relentless gravitational pull. This composition solves a practical mystery: how such a system can hold together without instantly flying apart. Lower mass stars and brown dwarfs exert gentler gravitational tides, creating fewer destabilizing waves within the system's delicate choreography. They are the stabilizing ballast in the cosmic ship, allowing the more massive, brilliant stars to anchor the whole arrangement without tearing it asunder. This revelation shifts our understanding from a spectacle of light to an architecture of gravity, where darkness plays as crucial a role as brilliance. But it raises a profound new question. If the system is built from such a variety of stellar bodies, each with its own history and fate, what kind of planetary environments could possibly survive within that gravitational web? The chaotic gravitational tides within a duodecuple system might seem like the worst possible nursery for new worlds. Conventional wisdom suggests that the competing pulls of 12 stars would shred any nascent protoplanetary disk, scattering the dust and gas needed to build planets into the void. Yet nature finds a way, and in this extreme environment, it forges planets of a truly alien breed. These systems do not simply destroy the raw materials for planets, they redistribute them in a grand act of cosmic recycling. The fierce gravitational interactions act like a colossal blender, pulling material from the outer reaches of individual stars and hurling it into new, unexpected orbits. While a disk around a single star might be torn apart, that material does not vanish. Instead, it can be funneled by the complex gravitational web into stable regions, most notably around the system's overall center of mass. This is the Lagrange point on a monumental scale, a calm eye in the hurricane of stellar motion. Here, far from any single star, a new, vast reservoir of dust and gas can accumulate, forming a circumsystem disk that belongs to the entire stellar family. From this shared disk, something extraordinary can coalesce, planets that orbit not a star, but the system's central balance point. Imagine a world born in this communal cloud. Its sky would contain not one, not two, but a dozen suns of varying sizes and colors, some locked in tight pairs, others drifting as solitary beacons. Their light would cast a kaleidoscope of shifting shadows, with days that never grow truly dark as one sun or another is always above the horizon. The concept of a year would be almost meaningless, replaced by an immensely long orbital period around the distant, invisible gravitational center. These would be the ultimate outsider planets, watching the intricate dance of their stellar parents from a serene and distant grandstand. Their formation is a testament to gravity's dual nature, both a destructive force and a master architect, capable of building stable order from the brink of chaos. But if such a world could exist, what would it be like to stand on its surface, and what new mysteries would its impossible sky reveal about the laws that govern all of reality? The very concept of a stable orbit is rewritten in this stellar metropolis. For a planet that manages to form within the gravitational sphere of a single binary or triple star subsystem, its path through space is anything but a simple repeating ellipse. Instead, it is a path of constant correction, a wobbling, processing dance dictated by the relentless pull of its distant stellar neighbors. Imagine swinging a pendulum, but every few seconds, an invisible hand gives the string a slight, persistent nudge from a different direction. The pendulum still swings, but its plane of motion slowly rotates, tracing a rosette pattern in the air. This is orbital precession, and in a duodecuple system, it is not a subtle effect, it is a dominant feature of existence. A planet's orbit does not just gently shift, it can tilt, warp, and change its orientation over spans of time that are short by cosmic standards. The gravitational tugs from the other 9 or 10 stars in the wider system act like a persistent, multi-directional breeze on a spinning top, causing its axis to slowly circle. Over centuries or millennia, the planet's entire orbital plane could flip relative to its host stars. One era might see the planet orbiting in the same flat plane as its binary suns, the next might see it looping over their poles. This has a consequence far more dramatic than a changing skyline. It completely redefines the idea of a habitable zone. On Earth, our temperate band of possibility is a relatively fixed ring around our sun. In a duodecuple subsystem, the habitable zone is not a location, it is an event. As the planet's orbit precesses and wobbles, its distance from its host stars changes drastically. It might spend 1,000 years in a comfortable, life-friendly range, only to be pulled slowly inward toward blistering heat or outward toward deep freeze by the combined gravity of the other stars. The zone of liquid water does not sit still, it moves like a spotlight across the solar system, and the planet must chase it along its chaotic path. Climates would not shift with the seasons, they would shift with the orbital epoch. Entire oceans could freeze over for millennia, then thaw into global tropical storms as the world drifts back into the warmth. The geological and, hypothetically, biological history of such a world would be written in cataclysmic chapters of climate upheaval, all driven by the silent gravitational music of a dozen distant suns. This raises a haunting possibility for any life stubborn enough to cling to such a world. How would it perceive the cosmos when its very sky is a clockwork of profound and terrifying change? That iconic image of a double sunset on Tatooine is a peaceful fantasy compared to the celestial reality of a 12-star sky. The problem of telling time, of understanding day and night, becomes a beautiful and unsolvable puzzle. You would not simply watch two suns set, you would witness a staggered, never-ending celestial ballet. The closest binary pair might dominate the sky as a single, brilliant orb, while a fainter triple system glows with a distinct combined light off to the east. As that primary binary dips below the horizon, another star, perhaps a solitary red giant, might be reaching its zenith, bathing the landscape in a deep amber glow. Eclipses would be a common, chaotic spectacle. One star could pass in front of another, dimming its light briefly, while a third star simultaneously emerges from behind a fourth. The patterns of light and shadow would be impossibly complex, with multiple, soft-edged shadows radiating from every object, each pointing toward a different sun in the sky. The very concept of high noon vanishes, replaced by moments where the overlapping light from several stars creates a surreal, shadowless brightness from all directions. True darkness would be a forgotten memory. Even when the brightest few stars have set, the cumulative glow from the remaining suns, however dim individually, would create a perpetual multi-hued twilight. The night sky would not be black, but a deep, luminous indigo, constantly shifting in color as different stellar combinations wheel overhead. This eternal, low-level illumination would come from every point on the compass, erasing the simple, singular directionality of a shadow. For any hypothetical life there, navigation by the stars would be an exercise in supreme patience, untangling a clockwork of dozens of moving points against a sky that never truly sleeps. This relentless gravitational interplay has a violent, creative flip side. While the hierarchical structure provides stability for the system as a whole, the individual stars within it are constantly jostling for position. Over millions of years, the intricate dance can falter. When two stars from different subsystems make an unusually close pass, their gravitational encounter is not a gentle nudge, it is a cosmic game of crack the whip. The physics is that of a gravitational slingshot, where a star can steal orbital energy from its partners. Imagine two dancers spinning, who briefly grab hands and fling each other apart with tremendous force. In a duodecuple system, this slingshot effect is amplified by the sheer number of participants. A star, often a smaller, lower mass one, can be whipped through a series of close encounters, each one accelerating it further, like a pinball bouncing between gravitational bumpers. If it gains enough velocity, it achieves escape velocity for the entire system. In a final, spectacular release, it is hurled out into the galactic void, never to return. This is the birth of a hypervelocity star, a runaway sun that can travel at speeds exceeding 1,000,000 miles per hour, racing across the galaxy on a lonely, one-way journey. These duodecuple systems, then, are not just serene celestial ballets, they are also volatile stellar factories. They can forge new planetary orbits in their shared disks, but they can also violently give birth to these stellar projectiles. Each ejection leaves a permanent scar on the family, altering the balance of the remaining stars, potentially triggering new rounds of instability that might fling out more members over eons. It is a process of self-pruning where the system sacrifices some of its members to maintain a stable configuration for the survivors. So, while we marvel at the intricate order of 12 stars bound together, we must also see them as cosmic catapults, capable of launching their own siblings into the great dark between the galaxies. This dynamic raises a compelling question about the very material that makes up these stars. Could the violent interactions within such a crowded system alter their fundamental chemistry? The chemical fingerprints of these stars hold the secret to their violent past. This brings us to a profound mystery at the heart of every complex system. Did they all form together as one family, or is this a cosmic orphanage built by capture? Astronomers call this the puzzle of co-formation versus dynamical capture, and the answer reshapes the entire story of the system's life. The evidence for a shared birth is compelling. If all 12 stars condensed from the same colossal, turbulent gas cloud, they would be chemical siblings. They would have nearly identical blends of heavy elements like lithium or iron, forged in the same stellar nursery and mixed into the same primordial soup. Their ages, measured by subtle changes in their light, would also match, telling a story of a single, explosive genesis event. Finding a duodecuple system where every member shares this chemical and age signature would be the ultimate proof of co-formation, a snapshot of a single, impossibly fertile cloud giving birth to an entire stellar dynasty at once. But the universe rarely offers such clean answers. More often, the evidence points to a messier, more dramatic history. We look at the orbits and see stars moving in wildly different planes and directions, as if they were thrown together from unrelated parts of space. We analyze their light and find stark differences in their chemical makeup. One star rich in carbon, another poor in metals. This is the hallmark of capture. In the dense, bustling environment of a young star cluster, stars are born in close quarters. A pre-existing triple or quadruple system, drifting through this stellar city, can use its complex gravity like a net. As a single star or another binary passes too close, the system's combined gravitational pull can break the passerby, snatching it from its original path and binding it into a new, wider orbit. Over eons, a system could grow from 3 to 6 to 9 stars, each capture event violently rearranging the gravitational hierarchy. The captured star becomes a permanent but distinct member of the family, an adopted child with a different origin story written in its elemental blood. So, which is it? The truth likely lies in a hybrid scenario. Perhaps a core group of 4 or 6 stars formed together from one cloud, their chemistry a perfect match. Then, as this core family drifted through its birth cluster, it began capturing other stars or small systems that formed nearby, building itself up to the staggering count of 12. This would create a system with a mixed signature, a core of similar stars surrounded by captured outliers on strange, tilted orbits. Each new capture would send gravitational shockwaves through the existing order, potentially triggering the ejection of hypervelocity stars we discussed earlier, or flinging planets into new, chaotic paths. The system we see today is not a pristine creation, but a survivor, a gravitational empire built through both birth and conquest. This violent assembly process forces us to ask what other relics of chaos might be hiding in these systems, not among the stars, but in the dark spaces between them. This search for captured stars leads us to a quieter, darker possibility. The gravitational glue holding a duodecuple system together might not be 12 brilliant suns at all. It could be a family dominated by shadows, by objects that never truly learned to shine. This is the brown dwarf dominance hypothesis. Recall that many of these complex systems are not assemblies of stars like our Sun, but mixed collections where faint red dwarfs and failed stars outnumber the bright ones. The hypothesis takes this idea to its logical extreme. It suggests the most stable, long-lived version of a 12-body system might be one where the majority, perhaps 8 or 9 of the members, are brown dwarfs. A brown dwarf is a cosmic in-between, more massive than a planet like Jupiter, but not massive enough to trigger the sustained nuclear fusion that defines a true star. They are failed stars, glowing dimly with the residual heat of their formation before fading into near invisibility. And that is their secret strength in a complex gravitational dance. Their lower mass is the key. In the intricate choreography of a dozen bodies, every star exerts a pull on every other star. The more massive a star is, the more it can yank its neighbors off their delicate, predicted paths, introducing chaos. Replace several of those massive stars with brown dwarfs, and you dramatically lower the volume of the gravitational noise. The brown dwarfs exert a gentler, more predictable influence, acting as stabilizing ballast. They fill out the gravitational count of 12 bodies, but do so without the destabilizing fury of a dozen full-fledged suns. The system's hierarchy becomes easier to maintain, its intricate clockwork less likely to grind itself to pieces over cosmic time. This leads to a startling and humbling thought. We may have already observed such stable, dark families and completely misunderstood what we were seeing. Telescopes have identified loose collections of free-floating brown dwarfs drifting through space. Current theory often labels them as failed stellar nurseries, clusters of objects that formed alone and are now drifting apart. But what if some of these groups are not loose clusters at all? What if they are tightly bound, hierarchical duodecuple systems where the one or two true stars are so faint, or the brown dwarfs so numerous that from our vast distance, the entire arrangement looks like just a chance grouping of dim, isolated objects? Their subtle gravitational bonds, the slow, grand orbits that link them, are invisible to our snapshots in time. We see the individual trees but miss the carefully planted orchard. To confirm this, we would need to track their motions over decades or centuries, looking for the telltale synchronized drift that betrays a shared gravitational fate. The most stable 12-star system might be one we cannot easily see, a dark consortium where the failed stars outshine the successful ones in the only metric that matters, gravitational harmony. If such dark, stable families are the rule, it forces us to reconsider what happens when one of their few true stars does reach the end of its life and dies not with a whimper but a universe-shattering bang. The end of a star's life is rarely a quiet affair, and in a city of 12 suns, a single death can rewrite the rules for everyone. Stellar evolution becomes a chain reaction of cosmic violence. Consider a massive star within one of the inner binary pairs. After millions of years, it exhausts its fuel and dies in a cataclysmic supernova. The explosion unleashes a wave of energy and high-energy particles that washes over the entire system at nearly the speed of light. For the star's immediate binary partner, this is an apocalyptic event. The blast can strip away its atmosphere entirely, leaving behind a scorched, barren core where a vibrant world might have once orbited. The supernova's fury does not stop there. It hammers every other star in the system, bathing them in intense radiation that could scour away protoplanetary disks and sterilize any fledgling biospheres across light years of space within the family. But the drama is only beginning. The supernova does not just vanish, it leaves a relic. The corpse of that massive star remains, now either an ultra-dense neutron star or, if it was massive enough, a stellar mass black hole. This creates a staggering new reality. The system now contains a dark, incredibly dense gravitational anchor, an object with the mass of a star compressed into a sphere the size of a city, silently orbiting within the living family. Its presence is felt, not seen. It tugs on its companions with the same gravitational force as before, but now it is an invisible participant in the dance. Imagine the remaining stars, unaware, continuing their intricate orbits around a point in space that now contains a bottomless pit of darkness. This transforms the system's future. A neutron star or black hole in a tight orbit can begin to feed, pulling material from a living companion star. This process creates some of the most energetic phenomena in the universe, like brilliant X-ray binaries or pulsars that flash like cosmic lighthouses. The system becomes a laboratory for extreme physics, where the dead actively shape the lives of the living. Over eons, more stars will reach the end of their lives. White dwarfs, the glowing embers of sun-like stars, will join the dance. The system could eventually host a macabre collection, a gravitational museum containing main sequence stars, red giants, white dwarfs, neutron stars, and black holes, all bound together in a single, impossibly complex web. This mixed family of the living and the dead raises a profound question about stability. Can a gravitational hierarchy built for 12 living stars survive when some of those stars become infinitely denser, darker versions of themselves? This gravitational museum of living stars and dark corpses becomes the ultimate crucible for physics itself. Within the chaotic pull of 12 massive bodies, including the intense, pinpoint gravity of neutron stars or black holes, we find nature's most extreme laboratory for testing Einstein's theory of general relativity. This is not a gentle experiment, it is a cosmic stress test where relativity's subtle effects are magnified to an almost grotesque degree. Consider the precession of an orbit, that slow wobble we discussed earlier. Around a single star like our Sun, Mercury's orbit precesses by a tiny, barely measurable amount, a triumph of Einstein's predictions over Newton's. Now place a planet, or better yet, a smaller star, in orbit within a duodecuple subsystem that also contains a neutron star. The precession would not be a subtle drift, it would be a wild, lurching pirouette. The combined gravity of all the bodies, especially the intense, curved space-time around the dense remnant, would twist the orbit into a complex rosette pattern visible over just a few years, not millennia. This offers a crystal-clear signal to measure, a dramatic confirmation of how mass and energy warp the fabric of reality. Then there is the eerie phenomenon of frame dragging. Einstein predicted that a massive, rotating object like a spinning neutron star does not just sit in space-time. It twists it around itself like a spoon spinning in thick honey. In our solar system, this effect is infinitesimally small. But imagine a rapidly spinning pulsar, the ultra-dense, magnetized remnant of a supernova, as a member of a tight binary within the larger 12-star family. As it spins, it drags the very fabric of space-time around with it. Any object orbiting nearby, be it a companion star or a planet, would have its orbit subtly altered by this cosmic whirlpool. In a duodecuple system, this frame-dragging effect would not exist in isolation. It would interact with the frame-dragging and orbital pulls from all the other stars, creating a tangled web of relativistic influences that could, in theory, be untangled. By precisely tracking the orbits, we could see the fingerprint of spinning space-time itself. The most precise tools for this, however, would be the pulsars themselves. If the system contains even one of these stellar lighthouses, its rhythmic pulses become the perfect cosmic clock. As the pulsar moves through the wildly varying gravitational landscape of the system, the timing of its pulses would be minutely affected. When it passes behind a particularly massive star, its pulses will be delayed as the light climbs out of a deeper gravitational well, an effect called the Shapiro time delay. As it gets tugged by different members, the pulse rate would speed up and slow down in a complex pattern. By decoding these tiny timing variations, astronomers could essentially perform a gravitational scan of the entire system. They could map the precise masses and positions of all 12 bodies, even the invisible black holes or dark brown dwarfs, by how they distort the path of the pulsar's clockwork signal. A duodecuple system with a pulsar would be a gift, a ready-made instrument for weighing the unseen and proving, once and for all, how gravity works in its most extreme and crowded environment. It turns a celestial curiosity into the universe's own precision scale. The silent witness to this gravitational chaos is not the stars themselves, but the dust that fills the spaces between them. In any star system, leftover material from formation coalesces into vast, cold rings of debris, from tiny grains of silicate to mountain-sized asteroids. We see these in our own solar system as the faint zodiacal light, but point an infrared telescope at a complex multi-star system, and you often find something far more dramatic, not a serene ring, but a turbulent, sprawling cloud of dust. This is the infrared signature of a system in constant upheaval. In a duodecuple arrangement, these dusty debris disks are not peaceful relics, they are active war zones. The gravitational perturbations from a dozen suns act like a never-ending series of tidal forces, constantly stirring the pot. Orbits that would be stable for millions of years around a single star become chaotic and short-lived. Planetesimals, comets, and asteroids are yanked from their serene paths and hurled into new trajectories that cross the paths of countless others. The result is a shockingly high rate of catastrophic collisions. Imagine an endless cosmic demolition derby happening on a scale we can barely comprehend. Two icy comets, each the size of a small country, are pulled into a head-on collision. A swarm of asteroids, destabilized by the passing gravity of a distant binary, converges into a storm of shattering rock. These are not gentle mergers, they are violent, obliterating impacts that pulverize solid bodies back into clouds of fine dust and glowing vapor. For us, watching from thousands of light years away, this perpetual violence reveals itself in a strange and beautiful way, episodic brightening. The infrared glow of the warm, fresh dust created in a major collision can cause the entire system to flare in our telescopes. Sometimes, if the collision is immense enough, the flash of light can even be detected in the visible spectrum, a sudden, temporary new point of light in the constellation, marking the death of a world that never was. This means the system lives in a state of punctuated chaos, with long periods of tense gravitational maneuvering punctuated by sudden, brilliant fireworks of destruction. The debris disk is never allowed to settle, never allowed to quietly coalesce into new planets without interruption. It is a cycle of creation and annihilation dictated by the clockwork of 12 dancing suns, a stark reminder that in such a crowded neighborhood, peace is merely the quiet moment between collisions. That endless cycle of dust and collisions points to a deeper mystery, a gap in our cosmic map. For all our talk of duodecuple systems, of the physics and the possibilities, we must confront a humbling observational truth. We have not yet found one, not a single definitively confirmed system of 12 gravitationally bound stars has been published in the astronomical literature. This is not a failure of theory, but a testament to the sheer difficulty of the hunt. Our catalogue of stellar families is filled with wonders that push the boundaries. We know of septuple systems like AR Cassiopeiae, a tangled dance of 7 stars, and Nu Scorpii, another brilliant septet. These are breathtakingly complex, proving that hierarchies can sustain 7 suns in a stable configuration. Each discovery of a system with 5, 6, or 7 stars is a triumph, a stepping stone that shows the architectural principles work, but the leap from 7 to 12 is monumental. It requires not just more stars, but a deeper, more fragile hierarchy, and orbits so vast that a single human lifetime is but a blink in their celestial clock. The stars are there, the data is flooding in from missions like Gaia, which maps stellar motions with unprecedented precision, and TESS, which watches for the telltale dips in light caused by eclipses. The first true duodecuple system is almost certainly hiding in those petabytes of information, its signal a subtle whisper lost in the roar of a billion simpler stars. Its confirmation will require patience spanning decades, as astronomers painstakingly untangle overlapping light curves and measure wobbles that take centuries to complete. This absence, then, is not an end but the most exciting beginning. It means the ultimate discovery in stellar multiplicity is still out there, waiting. It means the next great announcement in astronomy could be the one that changes our textbooks forever, revealing the full, glorious extent of gravity's capacity for order. And when we finally find it, we will face an even more perplexing question, not just how it works, but what such a system can ultimately become over the deep, slow march of cosmic time. Gravity can carve out pockets of profound stillness even within the most crowded systems. This leads us to a stable arrangement so elegant it feels like a geometric secret, the Trojan star configuration. To understand it, we must first visit a concept born from the three-body problem, the Lagrange points. Picture a massive binary star pair, 2 suns orbiting their common center of gravity. There are 5 specific points in space around this dancing duo where the gravitational pulls and the centrifugal force of the system perfectly balance. 2 of these points, labeled L4 and L5, are especially magical. They lie along the orbit of the binary pair itself, one 60 degrees ahead of it in its path and one 60 degrees behind. At these points, a much smaller object, like a planet or a low-mass star, can be trapped. It will orbit the system's center in lockstep with the binary, forever maintaining that 60-degree angle, forming a stable, equilateral triangle in space. This is a Trojan configuration, named for the Trojan asteroids that shared Jupiter's orbit in similar gravitational safe harbors. Now, scale that idea up dramatically. In a hierarchical duodecuple system, it is entirely possible for a small red dwarf or even a brown dwarf to occupy the L4 or L5 point of a far more massive inner binary. This would not be a star orbiting another star, but a star orbiting a point in space defined by the dance of two others. It becomes a permanent celestial sentinel, a silent partner in a triangular gravitational pact. The true wonder emerges when we extrapolate this geometry across the entire system. Imagine an inner core of 2 or 3 massive binary pairs. Orbiting ahead of each of these binaries at their respective L4 points could be smaller companion stars. Orbiting behind them at the L5 points could be yet another set. You would have a celestial array of staggering symmetry, a geometric lattice of stars locked in gravitational harmony, where triangles of light echo each other across the void. This is not random chaos, it is gravitational architecture of the highest order. Such a configuration could provide phenomenal long-term stability as the Trojan stars gently shepherd each other, their positions reinforcing the system's balance rather than disrupting it. To stand on a hypothetical world within such an array would be to witness a sky of perfect moving patterns where stars travel in synchronized packs, maintaining eternal geometric formations as they wheel overhead. It transforms the system from a frantic dance into a slow, stately procession of stellar triangles, a cosmic ballet choreographed by the immutable laws of physics. The geometric perfection of Trojan stars offers one kind of stability, but other bonds within the system are far more intimate and transformative. Within the tightest binary pairs of a duodecuple family, a different kind of dance unfolds, one not of balance but of consumption. When two stars orbit extremely close to one another, their gravitational embrace becomes so powerful it can distort their very shapes, pulling stellar material from one body to the other in a cosmic transfusion. This is the process of Roche-lobe overflow, and in a system crowded with a dozen suns, it becomes a catalyst for stellar metamorphosis. Every star has a region of space called its Roche-lobe, a teardrop-shaped zone where its own gravity dominates. In a close binary, the two Roche-lobes touch at a single point, like two soap bubbles meeting. If one star swells up, as stars do when they age, its outer layers can spill over this gravitational watershed and cascade onto its companion. Material doesn't fall gently, it spirals in at tremendous speed, forming a searing hot accretion disk around the receiving star before crashing onto its surface. This stolen fuel can fundamentally change a star's life story. The most dramatic result is the creation of a blue straggler. Imagine an older star, a cooler red giant, in a tight orbit with a smaller companion. As the giant swells, it donates a flood of fresh hydrogen onto the smaller star. This massive infusion of new fuel reignites the smaller star's core with the vigor of youth. It becomes hotter, bluer, and more luminous than any star of its age should be, standing out in observations as a strange, youthful outlier in an old stellar population. It is a stellar vampire rejuvenated by its partner's sacrifice. But this transfer is not always a smooth siphon. The influx of hydrogen-rich material onto the surface of a dense, hot star like a white dwarf can build up until it reaches a critical pressure. Then, in a cataclysmic thermonuclear flash, the accumulated layer detonates. This is a nova, a brilliant eruption that can outshine its host star by 100,000 times for a brief, glorious period. In a quiet system, this is a spectacular but isolated event. In a duodecuple system, however, the gravitational tides from the other 10 stars constantly jostle these intimate binaries. A distant star's passing tug could compress the binary's orbit, accelerating the mass transfer. Another's gravity might tilt the accretion disk, causing material to fall unevenly and triggering eruptions sooner or more violently. The system becomes a network of interconnected pressure cookers where a gravitational nudge in one corner can light a fuse in another. These stellar transformations are not mere curiosities, they are the system's engine for chemical recycling. The material flung into space by a nova, enriched with heavy elements forged in the explosion, gets scattered into the communal circumsystem disk. That dust, containing carbon, oxygen, and iron, becomes the raw material for a new generation of planets or even stars, all within the same gravitational family. The system is not static. It is a constantly churning ecosystem where stars change each other's fates and where death provides the seeds for new creation. These intimate dances of stellar material are governed by a deeper, more mathematical music. When the orbital periods of celestial bodies lock into a simple, repeating ratio, a powerful and delicate force emerges: orbital resonance. This is the hidden metronome that can bring order to chaos or shatter it completely. In our own solar system, we see elegant examples. For every 2 orbits Neptune makes around the Sun, Pluto makes 3, a stable 3-to-2 resonance that has protected Pluto's path for billions of years. But scale that up to a duodecuple star system, and the potential for resonance transforms from a simple duet into a full cosmic symphony with a dozen unpredictable players. The possible resonant chains are staggering. One binary pair might orbit the system's core in a period exactly twice as long as another inner trio. A planet in a circumsystem orbit could be in a 3-to-1 resonance with a distant quadruple subsystem, meaning for every 1 lap the planet completes, the quartet completes 3. These are not random coincidences, they are gravitational feedback loops. When bodies pass near each other at the same points in their orbits over and over, their repeated, gentle tugs reinforce a predictable rhythm. This can create pockets of profound stability, clearing chaotic zones and locking orbits into safe, repeating patterns that persist for eons. The entire 12-star system could, in theory, be knitted together by a web of these integer ratios, a fragile gravitational harmony keeping the celestial metropolis from collapsing into anarchy. Yet this harmony has a terrifying fragility. A resonance is a balanced state, but not an unbreakable one. The very thing that makes a duodecuple system a resonant wonder, its crowded nature, also makes it perpetually vulnerable. Consider the gravitational influence of a passing star from outside the system, a stellar flyby. In a lonely system like ours, such an event is rare and its effects are often mild. But in a delicate resonant web, that external tug is like a hammer striking a finely tuned clock. The flyby's gravity delivers a sudden, asymmetric shock to the system. It might speed up one binary pair by a minuscule amount or tilt the orbital plane of another subsystem by a fraction of a degree. That tiny change is enough. The perfect 2-to-1 ratio between 2 orbiting groups is broken. Now, when they pass, their gravitational kicks no longer reinforce stability. They begin to push each other off course. The broken resonance cascades through the web. The destabilized pair begins to pull erratically on a third group with which it was also in resonance, breaking that lock as well. Like a chain of falling dominoes, the precise mathematical music unravels. What was a symphony becomes a cacophony of gravitational noise. Orbits that were stable for millions of years begin to warp and intersect. Close encounters, once avoided by the resonant rhythm, now become inevitable. The result is a rapid, systemic plunge into gravitational chaos. Binary pairs could be driven into mergers, planets ejected into the void, and entire subsystems flung onto wildly new paths. The elegant hierarchical pyramid crumbles under the weight of its own broken symmetry. This reveals the true, paradoxical nature of these extreme systems. They are both monuments to long-term order and ticking clocks of potential catastrophe, their fates hinging on the preservation of a mathematical melody written in the motions of the stars themselves. This violent churn of creation and destruction presents a paradox for planet formation. While a shared circumsystem disk might birth a few hardy worlds, the relentless gravitational tides make it incredibly difficult for planets to form and survive in stable orbits around any single star. But nature abhors a vacuum, and this chaotic environment offers a different kind of opportunity. It could become a galactic way station, a temporary haven for the universe's loneliest travelers, rogue planets. These are worlds not born around a star, but ejected from their home systems during gravitational upheavals, doomed to drift forever in the cold dark between the stars. A duodecuple system, with its deep and complex gravity well, acts like a cosmic net. As a rogue planet wanders too close, the combined pull of a dozen stars can break its motion, snatching it from its solitary path and pulling it into the family's gravitational sphere. The planet would not settle into a nice, neat orbit. Instead, it would be thrown into a chaotic, temporary dance. It might loop wildly around a single binary pair for a few thousand years, only to be snatched away by the gravity of a passing triplet and flung into a new, even more eccentric path around the system's outer reaches. Its journey would be a series of gravitational hand-offs, a guest bouncing between different stellar households. For a brief cosmic moment, this nomadic world would have a sky again. It would bask in the light of not one, but several suns, its frozen surface perhaps thawing temporarily as it swung close to a stellar pair. But this hospitality is never permanent. The same complex forces that captured it will, inevitably, eject it. A close encounter with another star or a subtle shift in the resonant web could give it a gravitational slingshot, hurling it back into the interstellar void with even greater speed than before. The duodecuple system becomes a factory for supercharged rogue planets, worlds that have tasted the light of multiple suns only to be cast back into the eternal night, carrying with them the unique chemical imprint of their temporary chaotic home. The chaotic capture and ejection of rogue planets is a drama written in gravity and motion, but the system also keeps a different kind of record, one painted in light and shadow. When a star in this crowded metropolis erupts, the explosion becomes more than a momentary flash. It becomes a tool for cosmic cartography. A nova detonation or a colossal stellar flare does not just send a single wave of light directly toward our telescopes. That brilliant pulse radiates outward in all directions, illuminating everything in its path. In a system teeming with a dozen stars and vast, swirling dust clouds, this light does not simply pass through, it interacts. First, it strikes the nearest clouds of dust, heating them and causing them to glow in infrared, revealing their shape and density, but the light keeps traveling. Months or even years later, that same initial flash of light finally reaches more distant dust structures located farther out from the erupting star. These dust clouds then light up in turn, like distant mountains catching the last rays of a sunset long after the valley below has gone dark. This is the phenomenon of a light echo. We see the direct light from the eruption arrive at Earth, and then, years later, we see a second, fainter ghost of that same event as its light finally reaches us after bouncing off a distant cloud. In a simple system, this might create one or two faint rings of light expanding slowly outward. But in a duodecuple star system, the environment is unimaginably complex. The initial flash illuminates not just one dust cloud, but dozens, each at a different distance and angle from the blast. It also strikes the atmospheres and reflective surfaces of the other stars in the family. The result is not a single echo, but a cascading symphony of them. Light echoes bloom from multiple points, expanding at different rates, overlapping and interfering with each other in a pattern that changes year by year. For astronomers, this chaotic light show is a treasure map. By meticulously tracking the arrival times and angles of these dozens of overlapping echoes, they can perform a feat of celestial triangulation. They can calculate the precise three-dimensional distances between the erupting star and every major dust cloud and stellar surface it illuminated. It is like using a flashbulb in a vast, dark cathedral and photographing the reflections off every pillar, statue, and distant wall to map the entire room's layout. A single stellar eruption in a 12-star system can, over a decade of observation, yield a complete three-dimensional blueprint of the system's inner architecture, revealing the true shapes of dust lanes, the hidden cavities around binary pairs, and the exact spatial relationships between stars that mere orbital calculations can only estimate. The violent death throes of one star become the flashlight that illuminates the secret geometry of its entire family, a final, brilliant act of revelation written across the years. That three-dimensional map of light echoes reveals the system's architecture, but to understand the stars themselves, we must listen to their inner music. Every star is a resonating sphere, humming with vibrations caused by turbulent convection in its outer layers. These are starquakes, and their study is called astroseismology. By measuring the tiny, rhythmic changes in a star's brightness caused by these quakes, astronomers can peer deep into its hidden heart, determining its density, composition, and age with astonishing precision. In a solitary star like our Sun, this creates a single, complex chord of resonant frequencies. Now place that star in a duodecuple system. The constant, changing gravitational pull from its 11 companions acts like a never-ending series of tidal forces, squeezing and stretching the star's surface. This relentless agitation is like a master percussionist constantly striking a giant bell. The star's natural oscillations are not just allowed to hum quietly, they are excited, amplified, and driven into a state of perpetual, heightened vibration. Each of the 12 stars experiences this same tidal forcing, but each according to its own mass, age, and internal structure. The result is not 12 separate songs, but a single, overwhelming cacophony of resonant frequencies that echoes across the entire gravitational network. One star might thrum with the deep bass notes of a red giant's slow pulsations, while a tight binary pair rings with the high, rapid frequencies of distorted, tidally locked suns. A blue straggler, rejuvenated by stolen fuel, would vibrate with the vigorous, youthful harmonics of a much hotter core. This collective stellar symphony would be a data stream of unimaginable richness and complexity. For astronomers, the challenge and the opportunity would be to disentangle this cosmic noise. By applying the precise mathematics of tidal forces and stellar physics, they could theoretically filter out the gravitational noise introduced by the companions and isolate the pure signature of each star's internal quakes. Success would yield a revelation far beyond what is possible for isolated stars. We would not just know the approximate age of the system, we would know the precise individual ages of each component, revealing if they are true siblings or captured strangers. We could map the internal rotation of each star, seeing how the tidal drag from its partners has spun up or braked its core. Most profoundly, we could detect the subtle vibrational fingerprints of elements like helium and hydrogen deep within their fusion zones, creating a detailed chemical profile for each dancer in the celestial ballet. This astroseismic symphony would be the ultimate diagnostic tool, turning the entire duodecuple system into a transparent laboratory where the internal secrets of a dozen different stellar lives are broadcast on a gravitational loudspeaker. But if we can hear the music of their interiors, what does that tell us about the silent, shared environment that cradles them all? The internal vibrations of these stars tell a story not just of their present but of their ancient origin. This leads us to a profound shift in perspective, where a duodecuple system is no longer merely a curiosity, but a piece of galactic archaeology. These rare, intricate structures are likely not products of the modern, sparse galactic disk. Instead, they are fossils, relics from the Milky Way's violent and crowded infancy. To find a stable system of 12 stars today is to look back over 10 billion years to an era when our galaxy was a denser, more turbulent place. The first giant molecular clouds that collapsed after the Big Bang were unimaginably rich and compact. Within these primordial nurseries, stars were not born in isolation, but in vast, bustling clusters where stellar siblings were packed shoulder to shoulder. In such a dense environment, the gravitational interactions necessary to build and bind a 12-star hierarchy were not just possible, they were probable. The young system formed deep within this stellar beehive, its complex architecture locked in place by the fierce gravity of its own members and the pressing crowd around it. But as the eons passed, the open cluster that birthed it slowly dissipated, its stars scattered by gravitational encounters into the growing galactic disk. The Duodecuple system, however, possessed a unique advantage: its deep gravitational bonds. While single stars and loose binaries were easily pulled away, this family of 12, with its layered hierarchy, acted as a single, incredibly massive object. It was far harder for passing stars to disrupt its intricate internal clockwork. So, as its birth cluster evaporated around it, the system endured, drifting into the galactic suburbs as an intact, functioning unit. Its survival for billions of years marks it as a cosmic artifact of incredible stability, a clock that has kept perfect time since the dawn of the galaxy. This makes it a unique window into that lost era. The chemical composition of its stars is a frozen sample of that primordial gas. By measuring the ratios of ancient elements like hydrogen, helium, and trace lithium within each member, astronomers could reconstruct the exact conditions of the original cloud, learning its temperature, density, and even the shock waves from the very first supernova that enriched it. Furthermore, the system's present-day motion through the galaxy is a clue to its past. Its path across the sky, its velocity, and its orbital trajectory around the galactic center are all echoes of the gravitational kicks it received in that long-vanished cluster. By tracing its motion backward through time, we could potentially locate the ghost of its birthplace, mapping the dispersal of one of the Milky Way's first stellar nurseries. A true Duodecuple system is therefore more than a gravitational marvel. It is a time capsule. It holds within its dance the memory of a younger, wilder universe, offering a direct link to the chaotic conditions that forged the first generations of stars and set the stage for everything that followed, including our own solitary sun. That deep time capsule holds a hidden clock, a slow and violent mechanism that can dismantle its own stability from within. This is the danger of Kozylidov cycles, a gravitational effect so subtle it operates on timescales of millennia, yet so powerful it can reshape the destiny of worlds. To understand it, picture a simple system, a planet orbiting a star. Now introduce a distant third star orbiting them both at a steep angle. This outer companion's gravity does not just pull, it twists. Over thousands of years, it orchestrates a precise and relentless exchange between two of the inner planet's orbital properties: its eccentricity, which is how oval-shaped its path is, and its inclination, the tilt of its orbital plane. When the planet's orbit becomes more circular, its inclination increases, tilting it higher. Then, as that tilt is pumped back down, the eccentricity skyrockets. The orbit is transformed from a near circle into a needle-thin ellipse. At its most extreme, the planet's path becomes so elongated that at its closest approach, it skims terrifyingly close to its host star, and at its farthest, it ventures out into the frigid depths where the outer companion lurks. In a calm, single-star system, this effect is minimal, but place this scenario inside a Duodecuple hierarchy, and it becomes a recipe for systemic chaos. Here, every star and planet is subject not to one perturbing outer companion, but to 10 or 11 of them. Each distant member of the stellar family can act as a driver for these Kozylidov cycles on different inner pairs or planets. The cycles overlap, interfere, and amplify one another. A planet in a stable, circular orbit around one binary pair might have its tranquility shattered by the gravitational influence of a quadruple subsystem orbiting several billion miles away. Over 50,000 years, that planet's orbit could be slowly pumped into a radical ellipse, turning it into a wrecking ball on a cosmic timer. At the peak of its eccentricity, its new path might cross directly through the orbit of another planet or even through the tight binary at the system's heart. The result is inevitable: a catastrophic close encounter, a shattering collision, or a gravitational slingshot that ejects the world into interstellar space. The most chilling aspect is the predictability. These are not random acts of violence, they are the consequence of celestial mechanics written in stone. Once initiated, a Kozai-Lidov cycle will complete its oscillation, driving the inner orbit to maximum eccentricity and back, over and over, like a slow-motion pendulum of doom. In a 12-star system, these cycles are the built-in clocks of instability, ticking away in the gravitational background, ensuring that no orbit, no matter how stable it seems today, is guaranteed peace tomorrow. They transform the system from a static monument into a dynamic, evolving engine of destruction, where the very bonds that hold the family together also contain the seeds of its own periodic upheaval. These slow-motion clocks of instability reveal a gravitational influence far greater than the visible light of 12 suns could ever account for. The most extreme possibility for a duodecuple system is not a family of stars, but a family anchored by darkness. This is the dark duodecuple hypothesis. What if some of the 12 components are not stars at all? We have already seen how systems might be dominated by faint brown dwarfs, and how a supernova could leave a black hole silently orbiting within the family. Now push that idea to its logical limit. Imagine a configuration where only 4 or 5 visible stars, perhaps a tight binary, and a few solitary red dwarfs trace wide, slow orbits around a seemingly empty point in space. Their motions, however, betray a terrifying truth. The speed and paths of these visible stars indicate they are whirling around a common center of mass containing an immense, invisible gravitational anchor, a mass equivalent to 7 or 8 suns. Yet our telescopes see nothing there. This suggests the core of the system is not a collection of failed stars, but something far more enigmatic. It could be a small cluster of stellar mass black holes, the remnants of massive stars that lived fast, died young, and now huddled together in the dark, their combined gravity dictating the dance of the living stars around them. Or, more mysteriously, it could be a concentrated knot of dark matter, that unknown substance which makes up most of the universe's mass but refuses to interact with light. In this dark scenario, the visible stars are merely the outermost ornaments on a Christmas tree whose trunk and branches are made of shadow. Their orbits become the only way to map the invisible architecture. A star would speed up as it swung close to the dark core, feeling the pull of the hidden giants, then slow as it climbed away. By tracking these velocity changes with exquisite precision, astronomers could weigh the dark heart without ever seeing it. They could even, in theory, detect if the dark mass is a single object or a cluster by seeing how smoothly the star's acceleration changes. A single, point-like black hole would create a clean, sharp gravitational field. A jostling crowd of several black holes or a diffuse cloud of dark matter would create a more complex, rippling influence on the passing star's path. This transforms the entire system into a natural laboratory for probing the most elusive stuff in the cosmos. The visible stars become test particles, their trajectories a high-stakes experiment in fundamental physics. Finding such a dark duodecuple arrangement would be one of astronomy's ultimate discoveries, forcing us to confront a profound and beautiful mystery, a cosmic dance where most of the dancers are permanently hidden from view, their presence known only by the graceful, obedient motions of the few who carry the light. The possibility of life must be reimagined under a dozen suns. Habitable zones are not fixed rings in these systems, but moving targets, shifting as gravitational tides warp planetary orbits over millennia. Yet within this grand instability, there might exist rare and precious epochs of alignment. A world could find itself, through the slow procession of its path, lingering within the temperate range of its primary stars for 100 million years, a geological age long enough for life to arise, evolve, and perhaps even thrive. This is not a permanent home, but a temporary oasis in a cosmic desert of extremes, a window of opportunity opened by celestial mechanics. The challenges for any biology that emerged would be unlike anything on Earth. First, the radiation. With multiple stars, some likely flaring ultraviolet monsters, the surface of such a planet would be bombarded by a complex, unpredictable cocktail of high-energy particles. Protective atmospheres and magnetic fields would be under constant siege, potentially stripping a world bare over time unless life found a way to shelter deep underground or underwater. Then consider the gravity itself. The variable pull from a dozen different directions would not just shift orbits, it would knead the planet's interior. This could drive hyperactive plate tectonics, with continents cracking and volcanoes erupting in rhythms tied to the distant stellar dance. The very ground would be alive with seismic stress, reshaping landscapes on a timescale life itself might have to race to match. Yet, this chaotic sky also offers a paradoxical bounty: energy. With one or more suns almost always above the horizon, true night might be a brief, rare event. Photosynthetic organisms, the potential foundation of any ecosystem, would have access to a nearly perpetual, though wildly fluctuating, source of light. They might evolve to be incredibly flexible, able to photosynthesize under the deep red glow of a distant giant, then rapidly shift metabolic gears to handle the blistering blue-white glare of a close binary pair. Life here would not seek steady rhythms, but would master resilience, adapting to a reality where the rules of sunshine, gravity, and climate are rewritten every few thousand generations. The ultimate question is not whether such a place could be Earth-like, but what utterly alien forms of survival might evolve in a world where the very heavens are a clockwork of beautiful, relentless change. Amidst this gravitational symphony, a far more violent and invisible force is also at play. The stellar winds and magnetic fields of 12 stars do not simply coexist, they clash in a perpetual electromagnetic war that envelops the entire system. Each star, from the hottest blue giant to the coolest red dwarf, blows out a stream of charged particles, its own solar wind, and each star is wrapped in a complex magnetic field, a giant, invisible force field shaped by the churning plasma in its interior. In our quiet solar system, the Sun's magnetic bubble, the heliosphere, stretches far beyond Pluto, forming a protective cocoon. But in a duodecuple metropolis, you have 12 of these bubbles, all inflating and colliding simultaneously. The result is a magnetospheric battlefield of staggering scale, where the supersonic wind from one star slams into the wind from a neighbor. A colossal bow shock forms, a standing wave of superheated plasma that could be larger than the orbit of Jupiter. These are not static walls, they ripple and shudder as the stars move along their complex paths, sending shockwaves of energy pulsing through the shared space. Even more dramatic are magnetic reconnection events. This occurs when the magnetic field lines from two different stars become tangled and then violently snap like overstretched rubber bands, reconnecting into a new, lower energy configuration. The energy released in that snap is immense, accelerating particles to nearly the speed of light and producing brilliant flashes of X-ray and gamma-ray radiation. In a 12-star system, these reconnection events would not be rare. They would be a constant fireworks display, with magnetic fields from multiple stars intertwining and explosively reconfiguring across distances that could span the entire gap between stellar subsystems. This creates a turbulent, system-wide magnetosphere, a chaotic sea of magnetic forces and high-energy particles that fills every corner of the gravitational hierarchy. For any planet caught within this maelstrom, the consequences are both beautiful and terrifying. The planet's own magnetic field, if it has one, becomes a target. Charged particles funneled along these system-wide magnetic highways can bombard the planetary poles, driving auroras of unimaginable intensity. The entire sky, from horizon to horizon, could shimmer with curtains of light in 1,000 colors, a permanent celestial light show powered by the magnetic fury of a dozen suns. But this beauty comes at a terrible price. A relentless particle barrage, especially during a major reconnection event, can act like a sandblaster on a planetary atmosphere. It can energize the upper air molecules so much that they achieve escape velocity, bleeding the world's protective blanket slowly into space. Over millions of years, a planet with an Earth-like atmosphere could be stripped down to a barren, irradiated rock, its potential for life erased not by gravity, but by the invisible electromagnetic wrath of its many parent stars. This reveals a new layer of peril, where even a world in a stable gravitational orbit faces an atmospheric apocalypse written in magnetism and light. That electromagnetic storm is not the only rhythm within the chaos. Amidst the swirling magnetic fields and colliding stellar winds, the system holds a deeper, more perfect cadence. The eclipses and transits within a Duodecuple family could form the most precise natural clock in the known universe. In our solar system, an eclipse is a rare and special alignment. But in a sky filled with a dozen suns moving on different orbital planes, such events are a constant, predictable part of life. One binary pair might eclipse each other every 3 days with atomic clock regularity. A more distant triple star could transit in front of another every 11 years. Each of these events, when viewed from our vantage point, creates a specific, measurable dip in the system's combined light. The timing of these dips is governed by the immutable laws of orbital mechanics. If you could observe them for centuries, you would have a celestial timepiece of staggering accuracy, its ticks and tocks marked by the passing shadows of stars. But this clockwork becomes truly phenomenal if the system contains a pulsar. A pulsar is a rapidly spinning neutron star, the ultra-dense remnant of a supernova that beams radiation like a cosmic lighthouse. Its pulses can be timed to microsecond precision over decades. In a Duodecuple system, a pulsar would not just be a clock, it would be a probe. As it moves through the intricate gravitational landscape of its 11 stellar companions, its pulse timing would change in subtle, predictable ways. The gentle tug of a brown dwarf in a wide orbit would cause a slight, periodic delay. The warp in space-time caused by a close-passing main sequence star would bend the path of its radio waves, creating another tiny shift. Over decades, astronomers could map the entire mass distribution of the system just by listening to the heartbeat of this one dead star. They could detect the presence of hidden planets, not by the wobble they cause in a star's light, but by the minuscule delay they impose on the pulsar's perfectly timed ticks as it moves around the system's center of mass. This precision goes even further. The pulsar's rhythm is so exact that it could sense the universe itself breathing. The passage of a gravitational wave, a ripple in space-time from a distant cataclysm like colliding black holes, would momentarily stretch and compress the space between the pulsar and Earth. This would cause its pulses to arrive a few billionths of a second early or late. In a quiet system, detecting that requires multiple pulsars, but in a Duodecuple system, the complex dance itself provides a baseline. The predictable gravitational pulls from all the known stars can be perfectly modeled and subtracted, leaving behind a cleaner signal, a quieter laboratory to listen for the faint whisper of space-time itself ringing. This transforms the entire arrangement from a celestial curiosity into a fundamental instrument, a clockwork so precise it can weigh darkness, map invisible worlds, and hear the echoes of the most violent events in the cosmos. That cosmic clockwork of eclipses and pulsar ticks gives us a precise map of motion, but to understand the stars themselves, we must dissect their light. This reveals the next monumental challenge, the spectral fingerprint chaos. Every star has a unique barcode, its spectrum. When starlight passes through a prism, it fractures into a rainbow crossed by thousands of dark and bright lines. These lines are the atomic signatures of the elements burning in the star's atmosphere: hydrogen, helium, iron, calcium. They tell us the star's temperature, composition, age, and even its gravity. For a single star, reading this barcode is straightforward. For a duodecuple system, it is an astronomer's nightmare. Point a telescope at such a system, and the light you collect is not from one source. It is a blended, churning soup of 12 different stellar spectra, all superimposed into one impossibly tangled mess. The problem is compounded by motion. Each of those 12 stars is whirling along its own unique orbit. As a star moves toward us, its spectral lines shift slightly toward the blue end of the rainbow. As it moves away, they shift toward the red. This is the Doppler effect. So now, imagine those 12 layered barcodes, each one constantly shifting back and forth at different speeds and rhythms. The lines from a fast-orbiting inner binary might be swinging wildly over a period of days. The lines from a wider, slower pair might drift over years. The lines from a solitary star on a tilted orbit might be shifting in a completely different pattern. The final spectrum reaching Earth is a flickering, shimmering palimpsest, a single document written by 12 different authors, each scribbling over the others with a pen that never stops moving. Untangling this requires more than a keen eye. It demands a new form of computational archaeology. Astronomers must create sophisticated algorithms that can model the light of 12 hypothetical stars, each with its own spectrum, temperature, mass, and a unique orbital path. The computer then runs millions of simulations, tweaking all these parameters, trying to find the one combination that, when blended together, perfectly matches the chaotic, shifting spectrum observed over decades. It is the ultimate puzzle where the pieces are not only mixed together but are also constantly changing shape. The analogy is perfect. It is like trying to identify 12 different singers in a choir from a single, blended recording, while all of them are running in circles around the microphone at different speeds. A tenor's note might momentarily align with a soprano's, creating a false harmonic. A bass line might get Doppler shifted into the baritone's range. Successfully isolating just one star's clean spectral signature from this mess would be a triumph. It would confirm its temperature, its mass, and through the precise pattern of its Doppler shift, the exact shape of its orbit. Doing this for all 12 would be a feat that could take a career. This spectral chaos is the primary reason why a definitively confirmed duodecuple system remains elusive. We might see the gravitational dance in the stars' motions and the eclipses in their light curves, but until we can read their individual chemical fingerprints from the blended light, the final, definitive proof remains just out of reach, a beautiful and maddening secret hidden within a rainbow. The spectral chaos we try to decipher is a symptom of a far more violent physical reality. Every body in that crowded system is being physically kneaded by gravity, a process that turns cold rock and even stellar plasma into a furnace. This is the extreme of tidal heating, where gravitational flexing becomes the dominant source of energy for worlds and stars alike. To understand its fury, look no further than Jupiter's moon Io. Tugged by Jupiter's gravity and the orbits of its sister moons, Io's interior is stretched and compressed so violently that it has become the most volcanically active body in our solar system. Its surface a constantly changing mosaic of erupting lava fountains and flowing rivers of molten rock. Now amplify that scenario by an order of magnitude. Place a rocky planet within the gravitational sphere of a duodecuple system. It is not being tugged by one giant planet and a few moons. It is being simultaneously stretched and squeezed by the changing pulls of a dozen different suns. The tidal forces come from multiple directions at once, and they change rhythm as the stars move along their complex paths. There is no respite, no stable configuration where the forces cancel out. The planet's interior is churned like butter in a relentless, multi-armed gravitational mixer. The The friction generated by this constant flexing would be apocalyptic. The rocky mantle would not just melt in patches, it could liquefy entirely. The crust, thin and brittle, would shatter under the strain, becoming a global network of fissures spewing superheated magma. This would not be a world with volcanoes, it would be a volcano, a single, roiling sphere of incandescent rock where continents are born and consumed in geological instants. Its atmosphere would be a poisonous shroud of volcanic gases, constantly replenished by planet-wide eruptions, its surface illuminated only by the hellish glow of its own molten skin and the shifting light of its many suns. It is a vision of a world where the very energy for its cataclysmic geology comes not from a radioactive core, but from the celestial dance happening overhead. But this violent heating does not stop at planetary bodies. Even the stars themselves are not immune. In a tight binary pair within the larger system, the two stars are so close that their gravitational embrace distorts their spherical shapes into teardrops. This tidal locking and flexing does not just transfer material, it stirs the stellar plasma to a frenzy. The magnetic fields of each star become tangled and energized by this constant motion. The result is stellar hyperactivity on a colossal scale. These tidally stressed stars would be prone to monstrous flares, explosions on their surfaces that release energy equivalent to billions of atomic bombs. They would belch out coronal mass ejections, titanic bubbles of magnetized plasma with frightening frequency. In a simple binary, these eruptions blast harmlessly into space. But in a 12-star metropolis, that ejected plasma does not travel into empty void. It slams into the stellar winds and magnetic fields of neighboring stars or rains down on any unfortunate planets in the vicinity. A single, powerful flare from one tidally heated star could trigger a chain reaction, its radiation and particles compressing the magnetosphere of a companion star, perhaps inducing a sympathetic eruption there. The system becomes an interconnected grid of stellar tempers, where a gravitational nudge in one corner can ignite an electromagnetic storm light years across. This means the habitability of any world is threatened from within and without, scorched by its own internally molten core and sterilized by the unpredictable fury of its hyperactive parents. The tidal forces that provide a bizarre, volcanic form of warmth also ensure that true, stable life would face an endless, double-barreled assault. This constant gravitational flexing and heating is a symptom of a deeper, more patient force at work within the stellar crowd. Every star in the system, as it moves along its complex path, does not travel through empty space. It plows through the gravitational wakes and influences of its 11 siblings. This creates a subtle but relentless braking effect known as dynamical friction. Think of a giant ship cutting through a calm sea. The vessel pushes water aside, creating a turbulent wake behind it. That displaced water exerts a drag on the ship, slowly sapping its forward momentum. In a duodecuple system, the stars themselves are the ships, and the sea they sail through is the combined gravitational field of all the other stars. When a massive star, perhaps a blue giant, moves through this crowded neighborhood, it does not just feel the direct pull of its closest partners. Its immense gravity distorts the paths of every other star it passes, creating a kind of gravitational wake, a slight overdensity of stellar motion trailing behind it. This wake, in turn, pulls backward on the massive star itself, acting as a brake. The effect is a slow, steady loss of orbital energy. Over millions of years, this dynamical friction causes the orbits of the heaviest stars to decay. They spiral inward, sinking toward the system's gravitational center. Meanwhile, the lighter stars, the red dwarfs and brown dwarfs, experience the opposite. They are the water being pushed aside by the giants. The gravitational interactions tend to give them little kicks, transferring energy to them and nudging them into wider, more distant orbits. The system, over eons, begins to sort itself gravitationally. It is a process of cosmic sedimentation. The dense, heavy members sink to the middle, forming a tight core of massive stars, while the lighter members drift outward to the fringes. This natural sorting could explain the architecture we might eventually observe. The core of a mature duodecuple system might not be a random mix, but a concentrated knot of the most massive and luminous stars, all circling each other in a ferociously tight and complex dance, surrounded by a halo of fainter, slower-moving dwarfs on vast, lazy orbits. This friction is the quiet hand that organizes the chaos, imposing a grand, slow-motion order based purely on mass. It suggests that the system we see at any moment is not its final form, but a snapshot in a billion-year process of gravitational distillation. But what happens when that dense core of massive stars, now packed tightly together by dynamical friction, begins to reach the end of its brilliant, short lives? That slow motion sorting by dynamical friction creates a dense, brilliant core of massive stars, a powder keg waiting for a single spark. The ultimate chain reaction in a duodecuple system is not gravitational but thermonuclear. When one of these giant stars in the tight inner core finally exhausts its fuel, it dies not with a whimper but in a supernova that can rewrite the system's destiny in an instant. The explosion unleashes two parallel catastrophes. First, there is the raw physical blast wave, an expanding sphere of radiation and high-energy particles moving at a significant fraction of light speed. This wave slams into the other stars in the core, scouring their atmospheres, stripping away protoplanetary disks, and bathing every corner of the system in sterilizing radiation. But the second effect is even more insidiously disruptive, the sudden, violent loss of mass. In a single apocalyptic moment, a star that contained the mass of 10 suns might shed 90% of itself, flinging it outward in the explosion. Its gravitational anchor in the system vanishes. The intricate orbital dance, a balance of pulls and pushes perfected over millions of years, is instantly shattered. It is like cutting the tightrope in the middle of a high-wire act. The remaining stars, suddenly feeling the loss of that massive pull, are yanked off their stable paths. Their orbits become chaotic, elliptical lurches. Close encounters, once avoided by the precise hierarchy, now become inevitable. This gravitational cascade can force two other massive stars, now on wild new paths, into a direct collision or a merger. It can fling smaller, lighter stars out of the system entirely, turning them into hypervelocity runaways. The entire architectural pyramid, built so carefully, begins to collapse inward under its own unbalanced gravity. Yet the terror does not end there. If another massive star in that destabilized core was already teetering on the edge of collapse, its fate could be sealed by the violence of its neighbor's death. The supernova's shockwave, a titanic wall of pressure traveling through space, could physically compress that unstable star's outer layers. This sudden, immense pressure might be the final push needed to trigger core collapse prematurely. Or the gravitational chaos following the first explosion could alter the second star's orbit, driving it into a close interaction with a companion that strips its outer layers, hastening its demise. The result would be a second supernova, perhaps just centuries or millennia after the first. This is a cosmic domino effect of the highest order. One stellar death begets another, each explosion further unraveling the gravitational tapestry, making a third or even a fourth collapse more likely. The system would enter a phase of punctuated stellar genocide, a fireworks display of self-destruction where each brilliant flash marks not just an ending, but the trigger for the next catastrophe. In a span of time that is brief by cosmic standards, the brilliant core of a dozen suns could be reduced to a chaotic scatter of neutron stars, black holes, and a few traumatized survivors, their once grand dance replaced by the silent, dark sway of relics. Such a cascade of supernova would leave behind a graveyard of dense, dark remnants, a silent monument to the system's violent past. But what if, amidst that chaos, something else had been watching? This brings us to a fascinating and purely speculative thought experiment, the alien megastructure paradox. If a civilization evolved within a duodecuple system, their entire concept of astronomy and engineering would be born from a sky of profound complexity. Their energy needs, driven by the constant gravitational and electromagnetic turmoil, would be staggering. To survive, they might need to master energy sources on a scale we can barely conceive. Imagine them contemplating a Dyson swarm, a vast constellation of energy collecting satellites orbiting a star to capture its total output. For us, that is a project of mythic proportions around a single sun. For them, the question is fundamentally different. Would they build one swarm around their primary star, or would they attempt to construct 12, weaving a web of megastructures that dances in harmony with the stellar orbits? The engineering challenges are beyond comprehension. Each collector would need constant, active stabilization to resist the gravitational tugs of 11 other suns. Their orbits would require constant correction, a ballet of thrusters fighting against the cosmic tide. The swarm itself would be vulnerable to the system's violent events. A supernova blast wave or a close stellar pass could shred it like tissue paper. Perhaps they would not build around the stars at all, but in the calm eye of the storm. They might construct their civilization within the stable Lagrange points of the most massive binaries, or even in the vast, cold spaces of the circumsystem disk, drawing energy not from one star, but from the ambient light and gravitational friction of the entire family. Their mastery of celestial mechanics would need to be perfect, predicting Kozai-Lidov cycles and resonant breakdowns millennia in advance to relocate their habitats before a shift in gravity renders them uninhabitable. This leads to a dizzying inversion of logic. The very existence of a stable, long-lived duodecuple system might not just be a home for life, but a prerequisite for a certain kind of civilization. Only a cosmic environment that presents such extreme, multi-layered challenges could drive a species to develop the profound understanding of gravity, energy, and orbital dynamics required to even contemplate stellar-scale engineering. Their testbed would be their own backyard, a laboratory of 12 suns where failure means extinction. So, if we ever did detect the signature of a megastructure, a strange, repeating shadow or an infrared glow that defies natural explanation, we might find it not around a quiet, solitary star, but in the last place we'd expect, in the brilliant, chaotic heart of a celestial family where survival itself is a testament to unimaginable ingenuity. The greatest monument a civilization could build might not be a swarm around a star, but the simple, enduring fact of their continued existence within the storm. The silent, spiraling dance of dead stars would fill the system with a music we cannot hear. Within a mature duodecuple family, the white dwarfs, neutron stars, and black holes left behind by supernova do not sit still. They continue their intricate orbits, but now as infinitely denser, darker versions of themselves. When these compact objects pair up in tight binaries, their dance becomes a death spiral. As they orbit, they lose energy by rippling the very fabric of spacetime itself, emitting gravitational waves. This causes their orbits to shrink slowly at first, then with increasing frenzy until they finally collide in a cataclysmic merger. In a typical galaxy, such an event is rare, a singular crash separated by millennia. But in a duodecuple system, it is different. You have not one potential pair of dead stars, but several, all orbiting within the same gravitational web. The result is not an occasional solo performance, but a constant, overlapping chorus. Multiple pairs of compact objects could be inspiraling at the same time, each at a different stage of their final dance. Their combined gravitational wave signals would create a persistent, low-frequency hum emanating from that single point in the sky, a background noise of space-time vibrations unique to this ultra-crowded stellar metropolis. This chorus would not be a steady tone, however. It would be a complex, modulated song. The reason lies in the hierarchy. Each inspiraling binary of dead stars is itself orbiting the system's center of mass, tugged by the gravity of the other 10 living stars. As this binary moves along its wider path, its gravitational wave signal would be altered by the Doppler effect, just like the pitch of a siren changes as an ambulance passes by. When the binary is moving toward us in its orbit, the gravitational waves get compressed, their frequency slightly increased. When it moves away, the waves are stretched, their frequency lowered. This creates a slow, predictable warble in the signal, a periodic modulation superimposed on the ever-quickening chirp of the merger itself. For a system with multiple inspiraling pairs, each would have its own modulation pattern, a fingerprint of its unique path through the stellar crowd. Decoding this complex signal would tell us not just about the merging objects, but about the architecture of the entire living system that surrounds them. It would reveal the masses and orbits of the other stars simply by how they warp the song of the dead. This is where future observatories enter the story, not telescopes that see light, but instruments that feel the tremors in space-time. Ground-based detectors like LIGO are tuned to hear the final, high-frequency shriek of merging stellar mass black holes or neutron stars. But the long, slow inspirals, the decades or centuries-long choruses from wider binaries, exist at frequencies too low for Earth's noisy environment. To hear them, we must go to space. The Laser Interferometer Space Antenna, or LISA, is a future mission designed to do exactly that. It will consist of 3 spacecraft flying in a giant triangle, millions of kilometers apart, using lasers to measure distance changes 100 times smaller than an atom. LISA's sweet spot is the low-frequency gravitational wave band, the exact register where the Duodecuple chorus would sing. As it scans the sky, it wouldn't just hear random mergers. It might pinpoint a source that isn't a single, clean chirp, but a sustained, warbling hum coming from one location. That signal would be the gravitational fingerprint of an entire system in slow motion collapse. By analyzing the modulations, the changing frequencies, and the possible harmonies of multiple overlapping signals, astronomers could theoretically reconstruct the system's layout. They could count how many compact binary pairs are present, estimate their masses, and even map their wider orbits within the family. The gravitational waves become a direct sonification of the celestial architecture, allowing us to hear the hidden structure of a place we may never see clearly with light. It transforms the system from a visual puzzle into a symphonic one, where the most violent events in the universe become the notes that reveal its deepest secrets. That gravitational symphony, however, is a future sound. Today, we hunt for these systems with light, and our greatest tool is a silent surveyor orbiting 1,000,000 miles from Earth. The Gaia spacecraft is performing a census of the galaxy, measuring the positions, distances, and motions of over 1 billion stars with a precision never before imagined. For the search for duodecuple families, Gaia provides a critical clue, something astronomers call proper motion. This is the tiny, slow drift of a star across the backdrop of the distant universe, its actual movement through space projected onto our sky. Think of it as watching a flock of birds against a faraway mountain range. If the birds are flying together, their proper motions will be nearly identical, a shared direction and speed. Now picture that flock not as separate birds, but as 12 birds all tied together with invisible strings of varying lengths. They are all moving in the same general direction across the sky. That is the proper motion of the entire bound system. But here is where the magic happens. Each star is also whirling around its partners within the system. That intimate gravitational dance introduces a tiny, additional wobble to its path. So while all 12 stars share the same broad drift, each one jitters slightly around that average path, tracing a minuscule, corkscrewing trail through space. Gaia's genius is its ability to detect these microscopic anomalies. It doesn't just take a single snapshot, it observes each star dozens of times over its mission, building up a precise map of its velocity. When astronomers sift through Gaia's colossal dataset, they look for these statistical ghosts, groups of a dozen stars that are close together in space, moving in the same direction, but each exhibiting a tiny, rhythmic jitter in its motion that cannot be explained by anything but mutual gravitational binding. It is like finding 12 leaves caught in the same river current, all floating downstream together, yet each one also spinning in a small, private eddy. The correlation of their jitters is the telltale signature. If the wobble of star A seems to be mirrored with a slight delay in the wobble of star B, it suggests they are an orbiting pair. Extend that pattern across 12 stars with multiple overlapping pairs and groups, and you have the fingerprint of a hierarchical family. This method does not require us to see the stars eclipsing or to untangle their blended light immediately. It lets the fundamental fact of their shared gravitational destiny, written in the pure geometry of their motion, point the way. Gaia's proper motion data is the first great filter, winnowing a billion stars down to a handful of candidate systems whose skies hold not one sun, but a dozen, all dancing to the same slow song across the galaxy. This shared gravitational sphere creates a frontier far beyond the orbits of the innermost stars. Enveloping the entire stellar metropolis would be a vast spherical shell of icy debris, a circumsystem Oort cloud of almost unimaginable scale. Just as our solitary sun is surrounded by a distant reservoir of comets left over from the solar system's formation, the combined gravity of 12 stars would shepherd trillions of icy planetesimals into a similar but far more tumultuous borderland. This cloud would not orbit any single star, but the system's common center of mass, a frozen archive of the primordial material that failed to coalesce into planets within the chaotic inner realms. The dynamics of this cloud, however, would be anything but frozen. Astronomers describe comet clouds as dynamically hot or cold. A cold cloud, like our own Oort cloud, is relatively placid, with comets on slow, stable orbits that rarely change. The Duodecuple version would be dynamically scorching, with 12 different gravitational engines churning within it. No comet's orbit is ever truly safe. The constant, subtle tugs from passing stellar subsystems act like persistent gravitational pinballs, gently nudging these icy bodies over millennia. A comet peacefully drifting in the outer darkness might feel the distant pull of a binary pair swinging through its region, receiving a tiny boost of energy that alters its path. A few million years later, the gravity of another passing triplet might give it a second nudge. These incremental kicks accumulate, slowly but surely stirring the entire cloud into a simmering frenzy. The result is a permanent state of cometary siege for the inner system, where a star like ours might experience a major comet shower every few 100,000 years. When a passing star ruffles our Oort cloud, the inner regions of a 12-star family would face a near-constant drizzle of icy invaders. Comets would be perturbed inward on a regular basis, their long, elliptical orbits bringing them screaming through the stellar neighborhoods. The skies of any inner planets would be frequently graced or terrorized by the brilliant glow of new comets, their tails lit by the combined light of multiple suns. This endless barrage would be both a source of danger and a potential delivery mechanism. These icy bodies could bring water and complex organic molecules to dry, inner worlds, repeatedly reseeding them with the ingredients for life. But they could also be agents of cataclysm, with impacts occurring on a timescale that makes recovery between events difficult. For any civilization evolving there, tracking these icy projectiles would not be a branch of abstract science, but a vital discipline of planetary survival, a constant watch on the volatile frontier governed by their dozen parent suns. That constant barrage of comets is driven by a deeper, more fundamental turbulence within the stars themselves. The magnetic fury of a star is not a fixed trait, it is a product of its rotation. A fast-spinning star churns its internal plasma like a dynamo, generating powerful magnetic fields that knot and snap, unleashing flares and peppering the surface with dark star spots. In a duodecuple system, this magnetic engine is often cranked to its maximum. The tightest binary pairs are the key. When two stars orbit extremely close, their gravitational embrace is so strong it can force them into tidal locking, where one star's rotation period becomes perfectly synchronized with its orbital period, just as our moon always shows the same face to Earth. But gravity does more than lock, it spins up. As the stars interact, gravitational friction can actually transfer rotational energy, causing one or both stars to whirl faster than they ever would alone. This rapid rotation supercharges the stellar dynamo. The result is a star transformed into a magnetic monster, its surface a constantly shifting map of giant, dark spots, its atmosphere laced with loops of superheated plasma, and its temper prone to violent, unpredictable flares that blast out X-rays and ultraviolet radiation with enough energy to strip the atmosphere from a nearby world. This phenomenon, called chromospheric activity, is well documented in close binaries, but in a system of 12, the effect does not remain confined to the intimate pairs. The collective gravitational field of the entire family acts like a persistent, multi-directional stir stick for the stellar plasma. Even a star in a relatively wide orbit, one that would normally spin down and grow magnetically quiet over billions of years, feels the relentless tidal tugs from its many siblings. Its rotation is constantly being perturbed, never allowed to settle into a calm, steady rhythm. This stirring can maintain or even reignite magnetic activity that should have faded eons ago. The consequence is a system-wide enhancement of stellar fury. You would not have just one or two hyperactive binaries. You could have a dozen stars, each exhibiting elevated levels of magnetic violence to some degree. The sky becomes a network of potential flashpoints. From our distant vantage point, such a system would glow persistently in high-energy wavelengths. X-ray observatories would see it as a bright, unresolved smudge, a single point of light that is actually the combined glare of multiple stellar coronae heated to millions of degrees by magnetic reconnection. In ultraviolet light, it would shine with an intense, harsh brilliance, the signature of chromospheres in a state of permanent agitation. This creates a pervasive, inescapable bath of high-energy radiation that fills the entire gravitational sphere. For any potential planets, this is a double-edged sword. The constant UV flux could provide a powerful, if unpredictable, energy source for atmospheric chemistry, potentially aiding the formation of complex organic molecules. But it also acts as a relentless eraser, breaking down those same molecules and threatening to ionize and strip away planetary atmospheres over geological time. Life, if it could begin, would need to find shelter not just from the variable light of 12 suns, but from an invisible, sterilizing rain that falls from all directions, a magnetic legacy of the star's endless gravitational dance. All this magnetic fury and gravitational complexity rests on a single, fundamental measurement we often take for granted: how far away it all is. To truly understand a duodecuple system, we must first know its distance with absolute precision. This is not a trivial task. It is one of the most daunting practical challenges in observational astronomy. For nearby single stars, we have a powerful geometric tool called stellar parallax. The principle is simple. As Earth orbits the Sun, a nearby star appears to shift its position slightly against the backdrop of much more distant stars. By measuring that tiny angular shift over 6 months, astronomers can use basic trigonometry to calculate the star's distance directly. It is the gold standard for cosmic cartography. But apply this method to a blended point of light containing 12 stars, and the clean geometry dissolves into a mess of overlapping uncertainties. The problem is one of resolution. Even with our best telescopes, a duodecuple system thousands of light years away appears as a single, slightly fuzzy smudge of light, perhaps spanning a minuscule fraction of an arcsecond in the sky. Within that smudge, the light from all 12 stars is blended. When we try to measure a parallax, we are not tracking the clean back and forth motion of one point source. We are trying to measure the subtle, combined shift of a dozen overlapping points, each one potentially moving in a slightly different way within the blend due to their own internal orbits. It is like trying to measure the precise movement of a single bird within a distant, swirling flock using only a blurry photograph. The parallax signal we get is an average, a compromise that may not accurately represent the true distance to the system's gravitational center. This inaccuracy cascades into every other calculation we try to make. Distance is the foundational ruler for the universe. If we get it wrong, everything else we deduce becomes untethered from reality. An underestimated distance makes the stars appear dimmer and smaller than they truly are, leading us to miscalculate their masses and life stages. An overestimated distance does the opposite, making them seem artificially luminous and massive. We might mistake a collection of modest red dwarfs for a group of brilliant giants, or vice versa. This uncertainty corrupts our models of the system's hierarchy, its energy output, and even its long-term stability. To overcome this, astronomers must become forensic accountants of light. They use secondary distance indicators, like the subtle properties of a star's spectrum that hint at its intrinsic brightness, or they search for a single, identifiable star within the blend, perhaps a variable star with a known true luminosity, to act as a standard candle. But each of these methods introduces its own assumptions and errors, layering uncertainty upon uncertainty. The parallax challenge is a stark reminder that before we can untangle the dance of 12 suns, we must first solve the deceptively simple puzzle of how far away the dance floor really is. The official name for a duodecuple star system would be an administrative horror. The International Astronomical Union, the body responsible for celestial nomenclature, has a logical but rigid system for multiple stars. In a simple binary, the two stars are designated with capital letters like star A and star B. If one of those stars is itself a binary, its components get lowercase letters, becoming R and AB. Now build that for a family of 12. You might start with the widest pair, calling them component A and component B. But component A is not a single star, it is a close binary. So its children become R and AB. Yet R is also a binary, splitting into R1 and R2. Following the rules, these become RA and RB. Already, we have a star officially designated RB, a name that sounds more like a confused gasp than a cosmic identity. Now imagine component B is a triple star. Its primary gets BA, but its two companions are a close pair orbiting each other, so they become BBA and BBB. By the time you have accounted for all 12 members, the final designation for the faintest, most distant star could be something like HD 123456 AB, a BBBCA, a string of letters that looks less like a name and more like a fragment of corrupted computer code. This bureaucratic tangle is a perfect, if absurd, reflection of the system's physical reality. The name itself becomes a map of the hierarchy, a nested set of instructions for navigating the stellar relationships. It is a testament to human ingenuity in cataloging chaos, but also a guarantee that no one will ever casually refer to these suns by their proper titles. Astronomers would quickly resort to nicknames, perhaps calling them the Chaos Cluster or the Dancing Dozen, while the official designation sits in a database, a monstrous and precise monument to the fact that some things in the universe are simply too complex for elegant labels. The sheer density of suns in such a system creates a perpetual celestial stage for sudden, brilliant, and often violent performances. This environment would be a transient event zoo, a menagerie of unpredictable flashes and fades that would keep any observatory in a state of constant, thrilling alert. Unlike the quiet, predictable skies around a star like our own, where a notable event might occur once in a century, here the drama is relentless. The most obvious actors are the cataclysmic variables, those tight binaries where a white dwarf siphons material from a companion. In a duodecuple system, these pairs are not isolated. Their behavior is constantly tweaked by the gravitational tides of their stellar neighbors. This could lead to more frequent and more violent nova eruptions as fresh fuel is dumped onto the degenerate star's surface. You would not just see one nova every few decades, you might witness several from different binary pairs within the same century, each explosion briefly outshining the combined light of its 11 sibling suns. But the zoo holds far stranger creatures. Consider the simple geometric act of one star passing in front of another from our point of view. In a calm system, this is a predictable eclipse. Here, with so many stars on intersecting orbital planes, such alignments are common, but they are also gateways to a deeper magic, gravitational microlensing. When a foreground star drifts precisely in front of a more distant star in the same system, its gravity acts as a natural lens, bending and magnifying the background star's light. For a few days or weeks, that distant sun would appear to brighten in a specific, symmetric curve, a telltale spike in the data. This fleeting event does more than create a light show, it is a direct probe of mass. The shape and duration of the brightening curve reveal the mass of the foreground star, even if that star is a dim brown dwarf or a solitary planet that would otherwise be invisible. In a 12-star system, these chance alignments would happen with surprising frequency, offering a free, ongoing census of dark and faint objects hiding within the family. Every microlensing event is a surprise discovery, a flashbulb illuminating a hidden member of the troupe. Then there are the temperamental flare stars, often red dwarfs, whose magnetic fields can snap and release energy equivalent to billions of atomic bombs in a matter of minutes. In a duodecuple system, these flares are not solitary outbursts, they are potential triggers. The blast of X-rays and ultraviolet radiation from a major flare on one star can slam into the atmosphere of a nearby companion, heating it, ionizing it, and potentially inducing sympathetic magnetic activity. A single flare could ignite a chain reaction across the system, a domino effect of stellar tempers flaring in succession. Monitoring this requires patience and perpetual watchfulness, because the next great eruption could come from any of a dozen different points of light at any time. The light curve from such a system would never be a flat, boring line. It would be a jagged, spiking electrocardiogram of a living, breathing, and intensely volatile celestial entity. For an astronomer, this is the ultimate reward and challenge, a sky that is never still, offering a new mystery with every night of observation, where boredom is an impossibility because the universe is always insistently putting on a show. The gravitational tides from within are not the only force shaping this stellar family's destiny. An even vaster, slower rhythm governs its life, the gentle but relentless pull of the galaxy itself. The entire duodecuple system, a single massive object in the eyes of the Milky Way, travels on a grand orbit around the galactic core, a journey taking hundreds of millions of years. As it makes this immense circuit, it does not move through empty space. It sails through the galaxy's spiral arms, plunges through the dense plane of the galactic disk, and occasionally skirts the edges of colossal molecular clouds, those dark, star-forming nebulae that dwarf entire solar systems. Each of these encounters exerts a subtle external tidal force on the system. Think of it as a ship on a long ocean voyage. The ship itself is a tightly bound structure, but as it sails, it encounters vast, rolling swells and powerful currents. These ocean forces don't break the ship apart instantly, but they constantly stress its hull and can, over a long enough voyage, slowly work fittings loose. The galactic tide works in a similar way. Its gravity is diffuse, a gentle gradient across the immense width of the stellar system, but it pulls more strongly on the side of the system nearer to the galactic center and more weakly on the far side. This differential pull creates a torque, a twisting force that acts most effectively on the system's outermost, most loosely bound members. A solitary red dwarf or a wide-orbit brown dwarf, already clinging to the family's gravitational sphere by a tenuous thread, feels this galactic tug most keenly. With each passage through the dense galactic disk or each close shave with a giant cloud, that distant star receives a tiny gravitational nudge. It's a minuscule amount of energy, insignificant over a human lifetime or even 1,000,000 years. But over the course of 1 billion years, as the system completes multiple galactic orbits, these nudges add up. They gradually pump energy into the outer star's orbit, stretching it, making it more elliptical and less bound. Eventually, after eons of this slow-motion prying, the star reaches a tipping point. A final, gentle galactic tug provides just enough extra velocity for it to achieve escape velocity from the Duodecuple family's grasp. It drifts away, not with a violent ejection, but with a quiet, graceful release, becoming a free-floating star in the galactic halo. This is the process of tidal evaporation, and it means the system is slowly, imperceptibly dissolving from the outside in. The tightly bound inner core of massive binaries might remain secure for tens of billions of years, but the sprawling outer halo of companions is being steadily stripped away by the galaxy's tide. The system we see today is therefore a snapshot in an unfathomably long process of dissipation. It is not an immortal monument, but a temporary congregation, its outermost members destined to be slowly peeled away by the grandest current of all, the silent flow of the Milky Way itself. The chemical history of these stars is written not just in their light, but in the subtle traces of a single, fragile element. Lithium offers a forensic clue to the system's hidden past. This light metal, forged in the Big Bang and in some stellar processes, is easily destroyed. At the relatively low temperatures found in a star's interior, around 2.5 million degrees, lithium nuclei fuse with protons and vanish. In a solitary, calm star like our Sun, this destruction happens slowly over billions of years as the lithium in the outer layers gradually mixes down into the hot core. But introduce a partner and the story changes dramatically. In a tight binary system, the gravitational tides between the stars act like a colossal spoon, constantly stirring their interiors. This tidal mixing pulls lithium-poor material from the deep, hot core up toward the surface, while dragging fresh, lithium-rich surface material down into the furnace. The result is a star that burns through its lithium reserves at an astonishing rate, appearing artificially old and depleted in an element that should still be present. Now amplify this process across a duodecuple hierarchy. You have not one binary pair, but multiple tight binaries and triple systems, all experiencing this tidal churning. Furthermore, the gravitational jostling from the wider stellar family could enhance the mixing even in stars that are not in the most intimate embraces. The system becomes a lithium destruction factory. If astronomers could somehow measure the lithium abundance in each of the 12 stars, they would find a startling pattern. The stars in the tightest binaries would show extreme lithium depletion, their surfaces nearly scrubbed clean of the element. Stars in wider orbits might show moderate depletion. And any solitary stars or extremely wide companions might retain more of their primordial lithium, like untouched witnesses to the chaos. This creates a chemical map of dynamical intimacy. By reading the lithium levels, we could trace which stars have experienced the most violent gravitational interactions over their lifetimes. A star with normal lithium might be a recent capture, never subjected to the intense tidal stirring of the inner family. A star with almost no lithium likely sits at the heart of the gravitational storm, locked in a dance that has churned its depths for eons. This single element becomes a clock and a diary, recording not just the age of the stars, but the intensity of their relationships. It turns the blended light of a dozen suns into a readable history, where the quiet chemistry of a forgotten metal whispers the secrets of a gravitational lifetime. That chemical map of lithium depletion reveals a history of gravitational intimacy, but the physical orientation of the stars themselves can be just as telling. Our solar system is a relatively flat neighborhood with planets orbiting in roughly the same plane, a relic of the spinning disk from which they formed. In a duodecuple system, that simple geometry is often shattered. The possibility of polar orbits introduces a staggering new dimension to the celestial architecture. Here, entire subsystems can be tilted at radical angles relative to each other. Imagine one tight binary pair, two suns whirling around each other in a flat disk. Now picture another binary pair, or even a quadruple system, orbiting the first pair not in the same plane but perpendicularly. Their orbital path loops over the poles of the first system, like a hula hoop held at a 90-degree angle to another. This is not a rare fluke. It is a likely outcome of the system's violent assembly through capture or chaotic early interactions. When a small star cluster or a pre-existing multiple system is gravitationally captured, there is no reason for its orbital plane to match that of its new host family. It gets locked into the dance at whatever angle it arrived, often a steeply inclined one. This polar configuration does more than create a mesmerizing sky. It introduces a profound stabilizing influence. The gravitational tug from a polar orbiting companion is not constant. It varies in a specific, rhythmic way as it loops above, through, and below the plane of the inner system. Over the course of a complete orbit, these tugs tend to average out. They pull the inner system one way, then the opposite way, creating a net effect that is far gentler than if the companion were orbiting in the same plane and constantly pulling in the same direction. This averaging effect can actually protect the inner system from extreme orbital precession or quasi-Lidov cycles that would otherwise tear it apart. The polar orbit acts as a gravitational regulator, its off-plane influence preventing the wild, eccentric swings that lead to collisions or ejections. For a hypothetical planet within the inner system, the sky would defy all earthly intuition. The two primary suns would rise and set along a predictable path on the horizon. But the polar orbiting subsystem would not follow that path at all. It would trace a vertical arc, appearing to climb directly up from one point on the horizon, pass high overhead near the zenith, and then descend vertically to the opposite horizon. Its light would cast long, sweeping shadows that rotate through the day, a moving sundial pointing to a sun that does not travel east to west but north to south. Seasons already chaotic from orbital precession would be further complicated by the changing angle of this polar light source, which could bathe one hemisphere in constant oblique glare for centuries while leaving the other in a deep, multi-hued twilight. This celestial geometry transforms the system from a two-dimensional clockwork into a three-dimensional sculpture in motion, where stability is found not in flatness, but in the careful, counterbalancing tilt of its constituent parts. The delicate geometry of polar orbits offers a powerful stabilizing force, but it cannot eliminate every threat in a city of 12 suns. At the extreme end of gravitational chaos lies an event of breathtaking violence, a direct stellar collision. In a system this crowded, the intricate dance is always one misstep away from catastrophe. While the hierarchical structure is designed to prevent such disasters, it is not a perfect shield. Over billions of years, the slow, cumulative effects of gravitational perturbations from outside the system, or a resonant chain reaction from within, can nudge two stars onto intersecting paths. What begins as a close gravitational encounter can, in a matter of orbits, turn into an unavoidable convergence. The stars, drawn together by their own immense gravity, do not simply bounce off each other like billiard balls. They engage in a final, fatal dance. In a grazing collision, they might sideswipe each other, tearing away massive streams of superheated plasma that spiral into a shared, searing envelope before the stars, now brutally scarred, recoil onto new, chaotic orbits. But in a full merger, the outcome is both destructive and creative. The two stars plunge into one another, their cores spiraling together through a maelstrom of gas. In a matter of hours, they cease to be two separate entities. The titanic forces involved mixed their material violently, like blending two paints with a cosmic stir stick. The result is a single new star born from the ashes of its parents. This newborn sun is almost always more massive than either original star, and it spins with ferocious speed, its rotation whipped up by the angular momentum of the collision. For a brief, glorious period, this merger product becomes the brightest object in the system. The collision unleashes a phenomenal amount of energy, erupting as a luminous red transient, a sudden, brilliant flare that can outshine the entire Duodecuple family for months, visible across the galaxy. As the fireball fades, it leaves behind a profoundly altered object. The new star's chemistry is a scrambled, enriched mix of its progenitors' interiors. Elements that were once buried deep in stellar cores, like helium and carbon, are now churned to the surface. This chemically peculiar star becomes a permanent monument to the violence that created it, a beacon signaling a permanent change in the family ledger. The system's count has been reduced not by a quiet ejection, but by a spectacular act of fusion. 12 stars become 11, yet this subtraction is not a simplification. The new, more massive, rapidly spinning star is an unpredictable element. Its intense magnetic field and powerful winds will now exert a new kind of influence on its siblings, and its eventual death as a supernova will be all the more catastrophic for the extra mass it carries. A collision does not bring peace, it resets the clock on instability, creating a new gravitational centerpiece that will write the next chapter in the system's turbulent history. The final, brilliant flash of a stellar collision does not vanish into the void. Its energy and the relentless output of a dozen young suns weaves a tomb of light around the entire family. In the system's fiery youth, it would have been encased in the very nebula that gave it birth, a colossal cloud of gas and dust. But this is no serene stellar nursery like the Orion Nebula. With 12 powerful engines of radiation and stellar wind burning within it, the cloud would be tortured into a shape of impossible complexity. The combined ultraviolet glare from stars of different sizes and temperatures would ionize vast, overlapping cavities in the gas, making it glow in ethereal reds and blues. The stellar winds, each blowing with a different strength and from a moving source, would carve tunnels and blow bubbles that collide and merge. The result would not be a single, smooth shell. It would be a filamentary labyrinth, a luminous spiderweb spun from light and plasma. Dense pillars of dust, reminiscent of the famous pillars of creation but on a far grander scale, would twist like strands of cosmic silk, pushed into spirals and arches by the competing pressures from multiple directions. Some filaments would stretch directly from one star to another, tracing the lines of magnetic or gravitational influence between them. This dusty spiderweb nebula would be a transient masterpiece, visible for only a few million years before the combined fury of the stars completely blows it apart. Yet, in that brief epoch, it would serve as the ultimate visual signature of such a system. From 1,000 light-years away, it would appear as a single, bewildering smudge in a telescope, a tangled knot of light that defies simple classification, hiding the Duodecuple heart beating within its radiant threads. The light from a Duodecuple system would not just be blended, it would be alive with rhythm and chaos. Nearly every star in that crowded family would be a variable star, its brightness changing for its own unique reasons. This creates a classification nightmare of almost artistic complexity. You would have eclipsing binaries where two stars regularly pass in front of each other, causing predictable, deep dips in light. You would have pulsating stars, giant spheres that rhythmically swell and shrink, breathing in and out over days or weeks. And you would have the utterly unpredictable flare stars, red dwarfs that can erupt without warning, spiking the system's total brightness in a matter of minutes. Each of these stars contributes its own signature to the combined light curve, the graph of the system's brightness over time. The result is not a simple, wavy line. It is a maddening superposition, a tangled scribble where a dozen different clocks are all ticking at once, some with metronomic precision, others with random, stuttering bursts. Imagine trying to listen to a symphony orchestra, but every musician is playing a different song from a separate room, and the volume of each instrument is constantly changing on its own schedule. That is the data stream astronomers would receive. Disentangling this cacophony to classify each star's specific type of variability would be a puzzle with dozens of interlocking pieces, where solving one corner of the mystery instantly reshapes the questions in another. A regular dip every 3.2 days might signal an eclipsing binary, but does that dip get shallower when a flare star erupts? Does the pulse of a Cepheid variable star speed up slightly when a distant companion makes its closest approach? The light curve becomes a cryptographic document where the key to decoding one star's behavior is hidden in the noise generated by all the others. This monumental task is more than bookkeeping. It is the essential work of diagnosing the health, age, and intimate relationships of every member of the family. By classifying the variability, you learn who is locked in a tight embrace, who is aging and unstable, and who is prone to violent magnetic tantrums. It is the process of learning the personality of each sun, not from its color or spectrum, but from the unique rhythm of its heartbeat written in light. Within that chaotic web of colliding winds and magnetic fury, a far more invisible and dangerous phenomenon emerges. The system becomes a natural and terrifyingly efficient cosmic ray accelerator. Cosmic rays are not rays of light at all, but atomic nuclei, mostly protons, hurtling through space at nearly the speed of light. They are some of the most energetic particles in the universe, and their origin has long been a mystery. A duodecuple system provides a perfect engine to create them. Picture the supersonic stellar winds from a dozen different suns, each a torrent of charged particles. Where these winds slam into each other or into the slower moving material of the interstellar medium, they create colossal shock waves, standing walls of plasma moving at millions of miles per hour. These shock fronts are nature's particle accelerators. A proton or electron drifting in the turbulent space between the stars can get caught in the magnetic turbulence near one of these shocks. It bounces back and forth, trapped between the approaching wall of plasma and tangled magnetic fields, gaining a little more energy with each crossing. Like a ping-pong ball caught between two rapidly closing paddles, it is boosted to incredible speeds. In a simple system with one or two shocks, a particle might eventually escape. But in a 12-star metropolis, it faces a gauntlet. Ejected from the shock front of one binary pair, it travels through the system only to encounter the shock front from another stellar wind, or perhaps the expanding, superheated shell of a centuries-old supernova remnant. Each new collision zone gives it another powerful kick. The particle can be reaccelerated over and over, its energy climbing to levels that dwarf anything our most powerful human-made colliders could ever achieve. The entire volume of the system becomes a multi-stage booster rocket for atomic nuclei. The consequence of this relentless particle acceleration is a pervasive, deadly fog of high-energy radiation. These ultra-fast cosmic rays do not travel in polite, straight lines. They spiral along the system's tangled magnetic field lines, filling every corner of the gravitational hierarchy. When one of these bullets finally escapes the system and strikes a cloud of cold hydrogen gas in the surrounding interstellar medium, it creates a secondary fireworks display. The collision produces a cascade of gamma rays and X-rays, causing that distant gas cloud to glow faintly in these high-energy wavelengths. From our vantage point, the entire region around the Duodecuple system would be surrounded by a diffuse, shimmering halo of gamma-ray light, a telltale signature of the particle carnage within. For any potential planets, this is an existential threat. A planet's magnetic field and atmosphere are its only shields against cosmic rays. Under a constant, intense barrage from this accelerator, those shields will be tested to their absolute limits. The particles would pierce down to the surface, continually irradiating the ground and any fragile chemistry happening there. It creates an environment where the very building blocks of life are under constant assault, where stability is not just a gravitational challenge but a nuclear one. This invisible accelerator reveals that the true danger in a city of 12 suns is not always what you can see blazing in the sky, but what you cannot see screaming through the dark spaces in between. That invisible cosmic ray accelerator is a ghost, felt but not seen. To map its source, we must trace the footsteps of the stars themselves, a technique known as the astrometric binary hunt. Even if a telescope shows only a single point of light, that point can hold a secret. Its path across the sky is not a perfect straight line, it wobbles. This tiny, rhythmic wiggle is the telltale sign of an unseen companion, its gravity causing the visible star to pirouette around their shared center of mass. In a duodecuple system, this principle expands into a breathtakingly complex truth. Every single star you see is not just a star, it is an astrometric binary or a ternary or more, with respect to the system's invisible gravitational skeleton. Each one wobbles not just from a single hidden partner, but from the combined pull of 11 other bodies. Its path across the heavens is a compound dance, a superposition of multiple, overlapping pirouettes. The primary sun in a tight binary pair wobbles rapidly from its close partner. That entire binary pair as a unit then wobbles more slowly as it orbits with another pair. That quartet, in turn, traces a grand, slow wobble around the system's ultimate center of gravity. It is a wobble within a wobble within a wobble. Detecting and disentangling these nested motions is the key to mapping the entire invisible architecture. It is like trying to reconstruct the shape of a mobile hanging from a ceiling by only watching how one of its many ornaments drifts in a gentle breeze. You must measure not just the drift but every tiny jitter and loop in that ornament's path, then work backward to deduce the number, mass, and position of every other piece that is pulling on it. For astronomers, this means collecting not just images but exquisitely precise positional data over decades. Missions like Gaia are doing this on a galactic scale, measuring the positions of 1 billion stars to micro-arcsecond precision. When focused on a candidate duodecuple system, this data reveals not a calm drift but a frenetic scribble for each point of light. The challenge is computational sorcery. Algorithms must test millions of possible gravitational configurations, models with 12 masses on 12 different orbits, until they find the one combination of wobbles that perfectly matches the observed scribbles for all 12 stars simultaneously. Success would give us a gravitational blueprint, a map of masses and orbits for every component, including the dark ones we cannot see. The faint, rhythmic tug of a brown dwarf on a red star or the silent anchor of a central black hole would reveal itself not in light but in the precise, patient geometry of a star's journey across the void. This astrometric hunt turns the sky itself into a sheet of graph paper where the universe has already drawn the hidden structure of its most complex families in the faintest of penciled lines. The very concept of a stable temperature is a fantasy in this stellar metropolis. This is the thermodynamic inequality, a state of permanent, radical imbalance where a single world exists not under one sun, but within a dozen overlapping and competing ovens. There is no gentle average, no global climate. Instead, every point on a planet's surface, every orbiting dust grain, is subjected to a wildly different recipe of stellar radiation. One hemisphere might be turned permanently toward a brilliant, close binary pair, its surface baked under a relentless blue-white glare. The opposite side of the world, meanwhile, might bask only in the deep, feeble warmth of a solitary red giant, a dim ember hanging low on the horizon. And in the vast twilight zones between, the light from 3 or 4 other suns of varying colors and intensities would mix into a surreal, multi-hued glow, each contributing a different wavelength of heat. This is not a uniform global warming. It is a patchwork quilt of thermal extremes stitched together by celestial geometry. The consequences for any solid body, be it a planet or a wandering asteroid, are both beautiful and brutal. The temperature differences from one side to the other would not be mere degrees. They could be hundreds or even thousands of degrees. Such a violent thermal gradient would unleash weather systems of mythic fury. The atmosphere, if one existed, would become a global heat engine operating at maximum fury. Superheated air from the blistering day side would scream toward the freezing night side, generating permanent, planet-encircling hurricane-force winds that never cease, only shift their paths as the stellar configuration slowly changes overhead. On an airless world, the inequality expresses itself through sheer physical stress. The rock itself expands under the intense heat on one face and contracts in the deep cold of the shadow, creating tectonic forces far beyond any tidal flexing. The crust would groan and shatter under this daily thermal pounding, likely fracturing into a global network of deep fissures. The planet would quite literally be tearing itself apart, not from gravity, but from the simple, unforgiving physics of uneven heating. For a smaller body, like an asteroid or a comet nucleus, the effect is even more direct and destructive. Tumbling through this chaotic lightscape, one side of the rock gets flash heated while the other remains in profound cold. This extreme thermal stress can cause the material to fracture explosively, a process called thermal disaggregation. The object doesn't need to hit anything. It simply comes apart under the unequal stare of its many suns, adding another cloud of dust to the system's perpetual debris disk. This thermodynamic inequality ensures that nothing, from a giant world to a tiny pebble, can ever find a peaceful, balanced state. It is a constant, grinding force of erosion and tumult, a reminder that in a sky with 12 rulers, the very idea of a comfortable, stable environment is the greatest cosmic illusion of all. The ultimate stability of a dozen suns may rest on a simpler, more elegant geometry. While we often picture binary stars as the universe's fundamental couple, the true building block of extreme multiplicity could be a trio. Hierarchical triple systems where a close binary is orbited by a distant third star are not just common, they are remarkably robust. Their three-body dance, when arranged with the right distances, possesses a gravitational harmony that resists chaos. This reframes our entire conception of a duodecuple family. Instead of imagining a fragile pyramid of 6 binary pairs, picture something far more sturdy, 4 independent triple systems, each a stable celestial unit in its own right, all engaged in a slow, grand waltz around a shared center. Each triple is its own miniature cosmos with its own intimate dynamics, its own eclipses, and its own gravitational story. The close binary at its heart provides a tight anchor, while the distant tertiary star acts as a gentle shepherd, its wide orbit adding stability rather than disruption. Now take 4 of these complete, stable triples and place them in a vast orbital configuration. Their mutual gravitational attraction is now between 4 substantial objects, not 12 individual, jostling points of light. This drastically simplifies the system's mental architecture. The furious complexity is contained within each triple, allowing the overarching structure to become more predictable. This perspective isn't just a neat simplification, it might reflect the actual pathway of formation. In the dense stellar nursery where such systems are born, it's easier to imagine the capture or co-formation of small, stable groups. A triple system, already a gravitational package, could be more likely to survive a close encounter with another triple, merging into a sextuple system, and so on. The hierarchy builds not from the bottom up with single stars, but from the middle out with pre-assembled stable modules. This means the night sky from a planet within one of these triples would be dominated by its own 2 or 3 suns, with the other 9 stars appearing not as a chaotic swarm, but as 3 distinct, brilliant points of light, each point itself a tight triple system, moving with stately slowness across the heavens. The fundamental rhythm of life would be set by its local trio, with the wider family providing a majestic, slow-changing backdrop. It suggests that to build something as immense as a 12-star metropolis, the universe prefers to work with proven, stable blueprints, stacking completed apartments rather than trying to weld individual rooms together in midair. The densest stellar environment we know of lies 26,000 light-years away in the violent heart of our own galaxy. There, in the grip of the supermassive black hole Sagittarius A star, stars are packed together with a ferocity that defies imagination. In that crowded nuclear cluster, stellar orbits are measured in mere light days, and close encounters are a constant fact of life. This is the ultimate multi-star environment, a gravitational pressure cooker where stars are born, jostle, and die in a space smaller than our solar system's outer reaches. A stable duodecuple system, then, might not be a bizarre outlier, but a scaled-down, ejected refugee from such a place. Its intricate hierarchy of 12 stars could be a surviving fragment, a piece of shrapnel from a dense cluster that once orbited perilously close to the galactic nucleus. In the chaos near the black hole, gravitational interactions are so fierce they can fling entire star systems outward at tremendous speeds. Imagine a hierarchical family of a dozen suns, bound tightly together, drifting through that stellar maelstrom. A close pass with another massive cluster or a gravitational kick from the black hole itself could give the entire system a boost, ejecting it from the galactic center on a long, slow journey into the galactic suburbs. The system we might find today, drifting in the relative calm of the galactic disk, would carry the architecture of its traumatic birth. Its tightly packed inner core, its complex resonant chains, even its possible population of stellar remnants, would all be frozen echoes of that extreme environment. It would be a living fossil, a miniature model of the galactic core's dynamics, but isolated and preserved for us to study in comparative peace. This connection reframes the entire search. Finding a true duodecuple system would not just be about counting stars. It would be like discovering a piece of the galaxy's violent heart, miraculously intact and delivered to our cosmic doorstep for examination. The frantic scribble of astrometric data and the chaotic symphony of blended light are just the prelude. Within the next decade, our view of these stellar metropolises will transform from inferring shadows to witnessing the architecture in daylight. The key is resolution, the ability to see not a single smudge of light, but to separate that smudge into its constituent suns. This is the promise of the next generation of giants, like the extremely large telescope. With a primary mirror spanning 39 meters, it will gather more light than all of the world's major research telescopes combined. But its true power lies in a technique called adaptive optics, which uses lasers to create artificial guide stars in the upper atmosphere, allowing the telescope to correct for the blurring effect of Earth's air thousands of times per second. The result is a view of the heavens with a clarity rivaling that of a space telescope. For a nearby candidate duodecuple system, this changes everything. Instead of seeing a single point, the LT could resolve it into a dozen distinct pinpricks of light. We would not just know they are there, we would see them. We could watch in real time over years as a close binary pair whirls around each other. We could track the slow drift of a distant tertiary star against the backdrop of galaxies. The hierarchical pyramid would cease to be a mathematical model and become a direct image, a family portrait of suns. This visual confirmation would allow astronomers to measure the colors and relative brightness of each member with unprecedented accuracy, immediately classifying which are brilliant giants, which are faint red dwarfs, and which might be the dark, failed stars that theory predicts. The era of duodecuple system science would shift from detective work to direct observation. Yet, seeing the stars is only half the story. To understand the full ecosystem, we must also find the planets that might orbit within this gravitational labyrinth, and for that, we must look to space. The Pluto mission, a space observatory designed by the European Space Agency, is not a giant eye, but an ultra-precise light meter. Its core mission is to find Earth-like planets around Sun-like stars by watching for the telltale periodic dip in starlight as a planet transits or passes in front of its host. In a simple system, this produces a clean, repeating dip, but apply Plato exquisite sensitivity to the light of a duodecuple system, and the data becomes a cryptographic masterpiece of overlapping signals. A planet transiting one star in a tight binary would cause a dip, but that dip's depth and timing would be altered by the light of its companion star. A circumsystem planet orbiting the entire family might cause a shallow, long-duration dimming as it begins its trek across the face of one star, only for the signal to be interrupted by a flare from another. Plato's strength is its ability to monitor hundreds of thousands of stars simultaneously for years, gathering a continuous, ultra-precise light curve. By applying algorithms designed to untangle these multi-layered signals, astronomers could, for the first time, detect the presence of planets within these extreme environments. They wouldn't just find them, they could characterize them, measuring their sizes and orbital periods, and beginning to ask which of these chaotic skies might hold a world in a temporary, gravitationally forged oasis. The combination of the LT's piercing vision and Plato patient, precise hearing heralds a new chapter. We are on the verge of moving from knowing that such systems could exist to studying a specific one by name, to mapping its streets, and perhaps to finding the worlds that call its impossible sky home. 50 strange discoveries, and we are left not with an answer, but with a profound question about our place in the cosmos. These duodecuple star systems, whether we have found one yet or not, serve as the universe's ultimate lesson in humility. They are a living rebuke to our desire for simple, clean models of reality. Every time we think we understand the limits of gravitational stability, or the pathways of planet formation, or the rhythms of stellar evolution, a system of 12 suns whispers a reminder that nature's imagination is vaster, wilder, and more inventive than our own. They are not merely astronomical curiosities, they are philosophical instruments, tools that pry open our assumptions about what is possible. They demand that we invent new mathematics to describe their resonant chains, new physics to model their magnetic wars, and new patience to observe dances that take centuries to complete a single step. In their exquisite, layered chaos, they represent a frontier where our textbook definitions break down. They force us to confront a beautiful and unsettling truth that chaos and order are not opposites but partners in an eternal cosmic dance. Within the apparent anarchy of a dozen competing gravitational pulls, a strict hierarchical order emerges. From the constant violence of colliding winds and stellar flares, a stable, luminous nebula can be woven. From the thermodynamic fury of a dozen different ovens, a temporary, life-giving oasis might be carved. These systems are monuments to persistence, proving that even in the most crowded, volatile, and seemingly unstable conditions imaginable, patterns can find a way to lock in, and delicate balances can hold for billions of years. They show us that the cosmos is not merely a void dotted with simple stars, but a canvas for architectures of staggering complexity, where stability is not a default state, but a hard-won, dynamic achievement. To ponder a duodecuple system is to witness the universe experimenting with its own fundamental forces, pushing them to their absolute limits to see what beautiful, enduring structures can be built on the very edge of collapse. They are a testament to the fact that the cosmos is far stranger, more crowded, and more creatively ordered than we ever dared to dream. The journey through these 50 strange discoveries is a map of the universe's most extreme imagination. We have traveled from the delicate hierarchy that prevents gravitational anarchy to the violent factories forging hypervelocity stars. We have seen how a dozen suns can weave a spiderweb nebula, orchestrate a symphony of stellar vibrations, and create a cosmic ray accelerator in the void between them. The unifying theme is one of chaotic beauty, where order emerges not in spite of the tumult, but because of it. Each discovery, from the lithium-depleted surfaces of tidally locked stars to the slow motion clocks of Kozai-Lidov cycles, reveals a cosmos that thrives on complexity. Duodecuple star systems, whether a confirmed observation or a theoretical limit, are more than astronomical curiosities. They are stress tests for our fundamental laws, pushing astrophysics to its boundaries and demanding we invent new mathematics to describe their resonant, multi-layered dance. They prove that stability is not a peaceful default, but a dynamic, hard-won achievement sculpted by relentless gravitational forces. So the next time you look up at a seemingly simple point of light in the night sky, remember the potential for dizzying complexity it may hold. Wonder what other impossible-seeming architectures are waiting in the darkness, their stories written in gravity and light, silently challenging our understanding. The ultimate lesson of the Dancing Dozen is to stay forever curious, for the universe's capacity for surprise is truly endless. So which of these 50 strange discoveries fascinated or baffled you the most? Was it the thought of a sky with 12 different suns, or the idea of a dark duodecuple system held together by invisible black holes? Let us know your thoughts in the comments below. I love hearing what sparks your curiosity. If you enjoyed this deep dive into the universe's most extreme stellar architecture, be sure to subscribe and hit the notification bell. That way you won't miss our next exploration of space mysteries, where we unravel the secrets of everything from colliding galaxies to the echoes of the Big Bang. To keep your cosmic education going right now, you can check out our videos on the violent lives of binary stars, the lonely journeys of rogue planets, or how we're learning to listen to the universe through gravitational waves. Thanks for joining me on this journey to the edge of what's possible. Until next time, keep looking up and wondering.